Welcome to Calm and Clever. It's lovely to have you here tonight. Wherever you are right now, whatever corner of the world you've curled up in, I'm glad you found your way to this little pocket of quiet. Maybe you're under a heavy blanket with the lamp still glowing soft in the corner. Maybe you're on a train watching the dark slide past the window. Maybe you're just lying there in the dark, eyes already half closed, letting the day finally let go of you. However you've arrived, you're welcome here. Settle in. There's nothing you need to do now except breathe slowly and let your shoulders drop a little.
Before we drift off into tonight's story, I'd love to know, where in the world are you watching from? Tell me, down in the comments, where you are and what time it is in your corner of the night. I always love reading them. It's a strange and lovely thing, isn't it? To think of all of us scattered across the planet, lying in our separate beds in our separate hours, all listening to the same quiet voice.
If you enjoy these slow journeys and want more of them, a gentle like and a subscribe really do help this sleepy little channel keep going. Small creators like me rely on that more than you'd think. And to those of you already subscribed, already part of this nightly ritual, thank you, truly. You're the reason I get to be here at all. Now I'll make you my usual promise. I'll try very hard not to make tonight's story so interesting that it keeps you awake. But if it does, well, at least you'll have learned something beautiful. That seems like a fair trade to me. So let's begin, shall we? Slowly, softly, one idea at a time. There is no rush tonight, and there is nothing you have to understand. If you drift off before the end, that's perfectly fine. The story will still be here, waiting when you wake. Tonight, I want to tell you the whole life of a star, the entire arc of it, from the cold, dark cloud where it's born, through the long, steady glow of its middle years, all the way to the very end, the final light, whatever shape that ending takes. It's one of the grandest stories the universe has to tell, and yet at its heart, it's surprisingly simple, because here is the strange and wonderful secret I want to leave with you tonight. The entire fate of a star, how brightly it will shine, how warm or how cool it will be, what color it will glow, how long it will live, and, most surprising of all, exactly how it will die. Almost all of that is decided in the very first moment of its life. It's written into the star at birth, and it's written by a single number. Just one number, its mass. How much matter the star is made of, that's it. That's the whole secret. If I could weigh a newborn star for you, I could tell you, with astonishing confidence, the entire shape of its life and the manner of its death, billions of years before either one arrives. The destiny is fixed at the start. The way the size of an acorn doesn't quite tell you it'll be an oak, but the mass of a star tells you almost everything. Now this is going to feel backwards in a way I think you'll find delightful, and we'll come back to it again and again as the night goes on, because you might expect that the biggest, brightest, most magnificent stars would also be the ones that live the longest. The grand ones, the showy ones, surely they last. But no, it's the opposite. The most massive stars are the most extravagant and the most doomed. They burn so fast and so fiercely that they live and die in a cosmic blink, sometimes just a few million years, while the smallest, humblest, dimmest little stars, the ones nobody would look at twice, those are the ones that go on practically forever. Bigger is not better. Out among the stars. Bigger means doomed. We'll see exactly why, slowly, as we go. And here's something to hold gently in the back of your mind as we drift through the story. There are 4 very different ways a star can die, 4 completely separate endings. One star might leave behind a slowly cooling cinder. Another might collapse into a single object so dense that a sugar cube of it would weigh more than all of humanity put together. Another might vanish into a hole in the fabric of space itself. And another might simply, quietly fade. 4 deaths. And which one a star gets is decided, you've guessed it, by that one number, its mass. In fact, it comes down to just a handful of precise thresholds, a few specific numbers, lines drawn across the scale of mass, and which side of those lines a star falls on at birth decides everything. There are really only 4 numbers that matter. I'll name them now softly, just so they're planted, and we won't fully understand them until much later. That's all right. Let them simply settle in like seeds.
0.08, 1.4, around 3 and 8, all measured in what astronomers call solar masses, that is, multiples of the mass of our own sun. Don't worry about remembering them. Just let them rest there, 4 little numbers floating in the dark. By the end of our journey together, you'll understand exactly what each one decides. For now, they're just a quiet promise of where we're going.
So, to understand how a star dies, we have to start at the very beginning. Before the light, before the warmth, before the fusion. We have to go to the place where stars are born. And it may surprise you to learn that stars are not born in fire. They are born in the cold, the deepest, darkest cold imaginable. Let me take you there. Out in the vast spaces between the stars, what astronomers call the interstellar medium, which is just a fancy way of saying all the thin, drifting stuff that fills the gaps. There are enormous clouds. We call them giant molecular clouds, and the name fits because they truly are giant. Some of them stretch across hundreds of light years, so vast that light itself, the fastest thing there is, would take hundreds of years just to cross from one side to the other. These clouds are the coldest, densest regions in all of space. And it's inside them, deep in their dark hearts, that new stars come to be. Now, when I say cold, I want you to really feel how cold. The temperature inside one of these clouds hovers somewhere around 10 to 20 Kelvin. Kelvin is just a temperature scale that starts at the coldest anything can possibly be, the absolute floor, the point where all motion stops. And 10 to 20 Kelvin is only a whisper above that floor. In the units you and I are used to, that's around minus 260 degrees Celsius. Think of the coldest thing you can imagine. Ice, deep winter, the frost on a window pane. This is colder than all of it. Colder, almost, than empty space itself. And out of this profound, almost unimaginable cold, the hottest objects in the entire universe are about to be born. Isn't that a lovely contradiction? The fire begins in the freezer. What are these clouds made of? Mostly hydrogen, the simplest, lightest, most common substance in all the cosmos. In these cold clouds, the hydrogen atoms have paired up into molecules, 2 hydrogen atoms holding hands, which is why we call them molecular clouds. About 90% of the cloud is this molecular hydrogen. Roughly 10% is helium, the next simplest element. And then there's a tiny sprinkle of something else, dust. Now, the dust is only about 1% of the cloud by mass, a mere trace. You might think something that makes up only 1% couldn't matter very much. But here's the gentle surprise. That little 1% of dust is absolutely essential. Without it, no stars could form at all. Because the dust does something the gas cannot do well on its own. It radiates heat away. It takes the warmth, the energy, the jittering motion of the cloud, and it lets that heat escape out into space as a faint infrared glow. Infrared just being a kind of light that's a little too red for our eyes to see, the kind of warmth you feel from a fire even with your eyes closed. The dust quietly sheds the cloud's heat into the dark, like a window letting the warmth of a room leak out into a winter night. And by cooling the cloud, the dust lets it grow colder and quieter and stiller. And a cold, still cloud is exactly what's needed for the next step. So that humble 1% of dust is the unsung hero of every star's birth. Hold on to that. The small things matter. For a long time, a cloud like this can simply sit there, vast and cold and patient, doing nothing in particular for millions of years. It's held in a kind of standoff. There are two forces wrestling inside it, very gently, very slowly. On one side, there's gravity, always pulling inward, always trying to draw the cloud together, to make it collapse in on itself. And on the other side, there's pressure. The gentle outward push of the gas, the way any gas naturally wants to spread out and fill the space it's in. For a long time, these two are evenly matched. Gravity pulls in, pressure pushes out, and the cloud just hangs there in balance, neither collapsing nor flying apart. Asleep, you might say. But this balance is delicate. And there's a threshold, a tipping point. Astronomers call it the Jeans mass, named for the physicist who worked it out. And it's a beautifully simple idea once you slow down with it. The Jeans mass is just the amount of matter you need to gather in one place before gravity finally wins. Gather up enough material, pack it densely enough, and gravity's inward pull becomes strong enough to overwhelm the outward push of the gas pressure. Cross that line, exceed the Jeans mass, and there's no going back. The balance breaks, gravity takes over, and the cloud begins to fall in on itself. The long sleep ends and the collapse begins. So what tips it over the edge? What gives a cloud that's been sitting peacefully for millions of years the little shove it needs to start falling? There are a few things, and they're all rather dramatic in their own quiet way. Sometimes it's a shock wave. Somewhere nearby, another star, an old, massive one, has reached the end of its life and exploded, sending out a great ripple of energy through space. That ripple, that shock wave, slams into the cloud and compresses it, squeezing parts of it together until they cross the Jeans threshold. So in a beautiful circular way, the death of one star can trigger the birth of another. The end of one life seeds the beginning of the next. We'll see much later in our story exactly how those grand stellar deaths happen. But for now, just hold the lovely thought that stars are born, in part, from the deaths of their elders. Sometimes the trigger is gentler. Our galaxy, the Milky Way, is a great spiral with long curving arms of stars and gas sweeping around its center. And as a cloud drifts through the galaxy, it can pass through one of these spiral arms, through what's called a density wave, a region where the matter of the galaxy is bunched up a little more thickly. Passing through that denser region can squeeze the cloud just enough to tip it over, like a slow ocean wave gathering loose sand together as it rolls up the beach. And sometimes, simply, two clouds drift into each other. They collide, slowly, softly, by our standards, and where they meet, the gas piles up and grows dense, and gravity finds its grip. A cloud collision, a quiet cosmic meeting that ends in new light. Whatever the trigger, once the collapse begins, things start to change. The cloud doesn't fall in all at once, evenly, like water down a drain. It breaks into clumps, knots of denser material, each one collapsing on its own, each one a seed for a future star. This is why stars are born in great families, in clusters, dozens or hundreds or thousands of siblings all forming together out of the same cloud. They're born like a litter, not one at a time. Now follow one of these collapsing clumps with me. Watch it fall inward. As it shrinks, something happens that you may have felt yourself on a playground long ago. Have you ever spun on an office chair or watched a figure skater turn and noticed how, when they pull their arms in close to their body, they spin faster. That's a real and deep law of nature, one of the most reliable laws there is. It's called the conservation of angular momentum. The amount of spin in a system is preserved, so if you pull the matter inward into a smaller space, it has to spin faster to make up for it. The skater pulls her arms in and whirls. The clump pulls itself in and whirls too. Every cloud has a little bit of spin to begin with, even if it's almost nothing, and as the clump collapses, drawing all that matter inward toward a center, that tiny initial spin gets amplified faster and faster. And here's the lovely consequence. A spinning thing that's collapsing doesn't fall into a perfect ball. The spin flings the material out to the sides, flattening it, so that the clump settles into a great flattened disc, wide and thin, like a record on a turntable or a pancake of glowing gas and dust, slowly turning in the dark. We call this a protoplanetary disk or a circumstellar disk, and at its very center, where the matter is piling up thickest and hottest, sits the heart of the future star. This flat, spinning disk is a quietly profound thing because it's not just the cradle of the star, it's the cradle of everything else too. Out in that disk, in the leftover material that doesn't fall all the way to the center, the planets will one day form, clumping together, grain by grain, into worlds. And this single fact explains something you can see for yourself on any clear night with a small telescope. It explains why, in our own solar system, all the planets orbit the Sun in very nearly the same flat plane, all going around in the same direction, like horses on a carousel. They didn't end up that way by chance. They were born from a spinning disk, and they still carry the memory of that spin billions of years later. Our whole solar system is the fossil of one ancient turning cloud. Isn't that something to drift off thinking about? That the orderly path of every planet was set by the spin of the cloud that made the Sun. But let's return to the center, where the real story is unfolding. That dense, hot heart at the middle of the disk. We have a name for it now. It's no longer just a clump. It's become a proto-star, a star-to-be, an almost star. But, and this is important, so let's go slowly, a proto-star is not yet a true star. Not really, because a true star, the kind that lights up the night, shines for one specific reason: fusion. Deep in its core, it's smashing the nuclei of atoms together, fusing them. And that process releases tremendous energy, which is what makes a star shine. A protostar isn't doing that yet. It's not hot enough at its center, not nearly. So why does it glow at all? Where does its light and warmth come from? It comes from falling, from gravity itself. As all that material rains down onto the protostar and packs in tighter, the act of falling, the act of compression, generates heat. You've felt a hint of this. Pump up a bicycle tire quickly and the pump grows warm in your hands because you're squeezing the air, and squeezing things heats them up. The protostar is being squeezed by its own gravity, enormous amounts of matter crushing inward, and all that crushing makes heat. This is called Kelvin-Helmholtz contraction, named after two scientists who first understood it, and it just means the heat that comes from a thing slowly collapsing under its own weight. So a protostar glows not with the true inner fire of a star, but with the warmth of its own falling. It's a star running on borrowed time, shining on contraction heat alone, waiting for the real fire to begin. And it waits a surprisingly long time. For a star like our Sun, this in-between stage, this restless adolescence before true starhood, has a name, the T Tauri stage, after the first star of this kind that was studied. And it lasts not for years, not for thousands of years, but on the order of tens of millions of years. Picture that. Tens of millions of years of a young star slowly contracting, glowing, churning, throwing off winds and flares, gradually growing hotter and denser at its core, inching ever closer to the moment of ignition. It's a long, slow childhood for an object that will go on to live for billions of years. There's no rush in the cosmos. The stars take their time being born, just as you're taking your time tonight, drifting down towards sleep. No hurry. The fire will come when it comes. And then at last, after all that slow contraction, after all those long millions of years of falling and heating, the center of the protostar reaches a critical point. The core temperature climbs to roughly 10 million Kelvin, 10 million degrees, a number so far beyond anything in your experience that it almost stops meaning anything. So let me just say it is unthinkably, ferociously hot, hotter than the heart of any furnace ever built, and the density at the core reaches around 150 grams per cubic centimeter, which is to say the matter there is packed so tightly that a single sip-sized spoonful would weigh more than a grown person, the hydrogen crushed denser than any metal you've ever held. And at that temperature, at that density, finally the magic happens. The hydrogen nuclei at the core, packed so close and moving so fast, begin to fuse. They slam together and merge, and in merging they release energy. The fire ignites. The star, at long last, switches on. And from that moment, it will shine with its own true light, not borrowed contraction heat, but the genuine, self-sustaining fire of fusion, the fire that can last for billions of years. But I have to pause here and tell you something genuinely astonishing, something that when you really sit with it is one of the strangest and most wonderful facts in all of physics. Because by the ordinary rules, the everyday common sense rules of how things should behave, the sun should not be able to shine at all. Here's why. Those hydrogen nuclei, the things that need to fuse together, each one carries a positive electric charge. And you might remember from somewhere long ago that like charges repel. Two positive charges push each other away, and the closer you try to bring them, the harder they push back, more and more fiercely. So to fuse two hydrogen nuclei, you have to force them right up against each other, against this furious repulsion, this invisible wall that grows stronger the closer you get. And here's the trouble. Even at 10 million Kelvin, even moving as fast as they do in the core of the sun, the hydrogen nuclei don't actually have enough energy to break through that wall. Not by the ordinary rules. They should approach, slow down, stop, and bounce harmlessly back, never quite touching. By classical physics, the physics of everyday things, of balls and ramps and the world you can see, the sun simply should not work. It doesn't have enough heat to force the fusion. The fire should never light, and yet there it is, shining in the sky every morning. So what's going on? The answer comes from the deepest, strangest layer of reality. The world of the very, very small, the world of quantum physics. And the particular piece of magic at work here is called quantum tunneling. Now, this is a peculiar idea, so let me set it down very gently. In the everyday world, if you roll a ball toward a hill and it doesn't have enough energy to reach the top, it rolls back down. Simple. It cannot get to the other side. But in the quantum world, the world of tiny particles, things are not so solid and certain. A particle doesn't have one exact position, one definite location. It's smeared out a little, fuzzy, more like a spread-out wave of possibility than a hard little dot. And because of that fuzziness, there's a small chance, just a small chance, that the particle will simply appear on the other side of the barrier it shouldn't be able to cross. Not over the top. Through it. As if a ball that couldn't climb the hill occasionally just turned up on the far side anyway, having passed clean through. That's quantum tunneling. The particle borrows a kind of impossibility and slips through a wall it has no business getting past. And this faint, ghostly, almost magical effect is the only reason the sun shines. The hydrogen nuclei can't break through the wall of repulsion by force, but every so often, by the strange grace of quantum tunneling, one of them slips through anyway and fuses with its neighbor and releases its energy. It doesn't happen often for any given pair. It's rare, but there are so unimaginably many hydrogen nuclei in the core of the sun, all jostling and trying, that even with each one having only a tiny chance, fusion happens steadily, reliably, enough to keep the great fire burning for billions of years. The sun is lit by a quantum loophole. The light that warms your face on a spring morning, the light that grew every plant you've ever eaten, all of it leaks into existence through a crack in the rules of reality. I find that almost unbearably beautiful. The most reliable thing in the sky runs on the unlikeliest trick in physics. So that's ignition. That's the moment a protostar becomes a true star. But, and here we come back to our one number, our mass. Not every clump that collapses out of a cold cloud manages to reach that moment at all. Because to get the core hot enough and dense enough to ignite hydrogen fusion, you need enough mass. Enough weight bearing down, crushing the core, driving up the temperature, and it turns out there's a minimum, a floor, a specific amount of mass below which the fire simply never lights. That floor is about 0.08 solar masses, 8/100ths of the mass of our Sun. In other terms, that's about 80 times the mass of the planet Jupiter. There, that's the first of our four little numbers, the ones I planted at the very beginning. 0.08, the ignition line. If a clump gathers up at least that much mass, gravity squeezes its core hard enough, hot enough, and the fusion fire catches. It becomes a real, true, shining star. But if it falls short, if it gathers up a little less than that, then no matter how long it waits, no matter how much it contracts, its core never gets hot enough, the fire never catches, and it ends up as something else entirely. We call those failed stars brown dwarfs, and I have a great deal of affection for them, these almost stars, these so close objects. A brown dwarf forms just like a star in collapsing from the cloud, contracting, heating, but it simply doesn't have the mass to finish the job. It can manage a brief, weak kind of fusion, burning a special heavy form of hydrogen called deuterium for a little while, but it can never fuse ordinary hydrogen, never ignite the true, long-lasting fire. So it just glows dimly with its leftover heat and very slowly cools, fading over the ages. A brown dwarf is a star that got all the way to the doorway of fusion and couldn't quite step through. So near. The difference between a star and a failed star can come down to whether it gathered up a little more or a little less material at birth. That one number again, mass, drawing the very first of its sharp lines. And here's a last gentle thought to rest on before we move deeper into the night. You might imagine that the universe is mostly full of grand, bright, magnificent stars like our Sun, or bigger. But it isn't. Not at all. When stars are born out of those cold clouds, the universe makes far, far more small ones than large ones. There's a pattern to it, a tendency astronomers call the initial mass function, and it's heavily tilted toward the small. For every great brilliant giant, there are countless little dim stars. The smallest, faintest, most modest stars of all, the ones we call red dwarfs. The galaxy makes far more embers than bonfires, far more quiet little nightlights than blazing beacons. Most of the stars in the sky, most of the stars that exist, are humble red dwarfs, glowing faint and red and steady, the modest majority of all the lights in the heavens. And here's the thing to carry with you, the thread will pick up again soon. Those humble little red dwarfs, the ones nobody would look at twice, the smallest and dimmest of all the stars. They are, by an enormous margin, the longest lived. They will outlast every great and glorious star in the sky. They will still be shining, faint and patient and red, long, long after the brilliant ones have flared and died. The meek, out among the stars, inherit the deepest reaches of time. But to understand why the smallest stars live nearly forever, while the grandest ones burn out in a cosmic instant, we have to turn now to that one number itself. We have to make mass the hero of the story and watch what it does once the fire is finally lit. Because everything that happens next, the whole long middle of a star's life and the manner of its ending, all of it flows from how much matter the star gathered in those first cold moments of its birth. Welcome to Calm and Clever. It's lovely to have you here, wherever you are tonight. Maybe you're under a heavy blanket with the lamp still on. Maybe you're on a train with the world sliding dark past the window. Maybe you've got a cup of something warm going cold beside you. It doesn't matter, you're here, and that's enough. And if you enjoy these slow journeys and you'd like more of them, a gentle like and a subscribe really do help this sleepy little channel keep going. Small creators like me lean on that more than you'd think. And to those of you already here, already part of this quiet little ritual, thank you. Truly. So tell me, while we settle in, where in the world are you watching from tonight? And what time is it in your corner of the dark? I always like to imagine you out there. Now, I'll try not to make this so interesting it keeps you awake, but if it does, well, at least you'll have learned something. A fair trade, I think. Here's the promise I want to make you tonight. There is one number, a single number, fixed at the very moment a star is born, that decides almost everything about it. How brightly it will burn, what color it will be, how long it will live, and which of 4 very different deaths it will one day meet. One number, that's the whole story really, and we'll take it slow, all the way through. Hold on to 4 little figures as we go. They're the secret thresholds, the gates the number has to cross. 0.08, 1.4, about 3, and 8. Solar masses, all of them. We'll come back to each. No need to memorize anything, just let them drift by like signposts in the dark. But before any star can have a number at all, it has to be born. And birth, out here, begins somewhere astonishingly cold. Picture a vast cloud drifting in the empty space between stars. Astronomers call it a giant molecular cloud, and it is the coldest, darkest, quietest kind of place there is. The temperature inside is around 10 to 20 Kelvin. That's about 260 degrees below zero in the everyday way of counting. Colder than anything you've ever touched. Colder, in fact, than the empty space around it. And out of this frigid stillness, out of the coldest places in the whole universe, come the hottest objects that will ever exist. Hold that strangeness for a moment. The fire begins in ice. The cloud is mostly molecular hydrogen, the simplest gas there is, 2 little hydrogen atoms holding hands. About 1/10 of it is helium, and then there's a whisper of dust, only about 1% of the whole thing by mass. Tiny grains scattered through the dark. But that 1% matters enormously. The dust is what lets the cloud cool by quietly radiating its warmth away as infrared light, letting the cloud sink colder and colder, denser and denser. The dust is the cloud's way of letting go of its heat so that gravity can finally take hold, and gravity is patient. For a long time, the cloud just sits there, balanced, its own gravity pulling gently inward, the faint pressure of its gas pushing softly out. A truce. But if a region of the cloud gets dense enough, heavy enough, it crosses a line. The astronomers call it the Jeans mass, the threshold where the inward pull of gravity finally overwhelms the outward push of the gas, and once you're past it, there's no going back. The cloud begins to fall in on itself. Something usually has to nudge it over that edge. Maybe the shockwave from a nearby star that has already died, exploding and sending a ripple through the dark. Maybe one of the great density waves that sweeps slowly around the spiral arms of the galaxy, gently squeezing everything they pass. Maybe two clouds simply drifting into each other in the deep. Any of these can be the little push. And then the falling begins. Now here's a lovely thing. As the cloud collapses, it spins. It was always turning, just a little, the way almost everything in the universe is. But as it shrinks, it has to spin faster. The same way a skater pulls her arms in and suddenly whirls. The physicists call this conservation of angular momentum, but you don't need the name, you just need the picture. The falling, spinning gas flattens out into a wide, turning disk with a thickening knot of matter gathering at the very center. That spinning disk is the reason, billions of years later, around some quiet little star, the planets all orbit in the same flat plane, all turning the same way. The shape of a solar system is set right here in the spin of the falling cloud. And that knot at the center growing heavier and hotter as more and more matter rains down onto it. That is a protostar. Not a star yet, not quite. It's glowing now, warm and red, but not from any fire in its heart. It glows only because it's shrinking, because falling matter releases heat as it falls, gravity slowly squeezing the protostar warm. The scientists call this Kelvin-Helmholtz contraction, which is just a careful way of saying it shines because it's being crushed. This is the long, restless childhood of a star, the T-Tauri stage, they call it, and for something the size of our sun, it goes on for tens of millions of years of just gathering and glowing and waiting for one thing, waiting for the core to get hot enough and crushed enough to finally catch fire. And that moment when it comes is exact. The center has to reach about 10 million Kelvin. The density has to climb to around 150 grams in every cubic centimeter. Matter packed so tight it's hard to even imagine. And here we come to one of the strangest, most quietly miraculous facts in all of this. By the plain rules of classical physics, the physics of falling apples and rolling balls, even that is not quite enough. The hydrogen nuclei, all carrying the same positive charge, push each other away so fiercely that they should never actually touch. By those rules, the sun should not be shining at all. It shines because the universe cheats a little in our favor. There's a quiet quantum trick called tunneling, where a particle can slip through a barrier it should never be able to cross, like walking through a wall that just occasionally lets you through. And every second inside the sun, countless hydrogen nuclei tunnel through that wall they could never climb and touch and fuse. Quantum tunneling is the only reason your sky has a sun in it at all. So now we have our threshold, the first of those four numbers. To light that fire and keep it lit, a young star needs at least about 0.08 times the mass of our sun. That's roughly 80 times the mass of Jupiter. Gather that much and you ignite. You become a true star. Fall short of it, even a little, and the fire never quite catches. You become something gentler and sadder instead, a brown dwarf, a kind of failed star that glows dimly and fuses a little deuterium for a while, but never manages real hydrogen fusion. Forever warm, never truly alight, just below the line. And now we come to the part that changes everything, because the number that had to gather, 0.08 solar masses, the ignition line, is only the beginning. Once a young star clears that threshold and hydrogen fusion catches in its core, it enters a new kind of existence. And the very first thing that existence tells us is something strange and slightly unsettling. Mass doesn't just decide whether a star is born, it decides everything that follows. Think about that for a moment, in the quiet wherever you are. The whole long biography of a star. How brilliantly it burns, what color it glows, how many billions of years it will last, and what kind of thing it will leave behind when it finally goes dark. All of it is set at the moment of birth by one single number. Not by where the star formed, not by what it's surrounded by, not by anything that happens to it later, just by how much mass gathered into that original collapsing knot of cold cloud. It's a little like being told at birth the exact story of your whole life, every chapter, every ending, sealed in that first moment. So let's follow that number. Let's see what it actually does. The first thing it does is control brightness, and it does so in a way that is wildly disproportionate. If you had a star twice the mass of our sun, just twice, you might expect it to shine roughly twice as brightly. That would feel intuitive. Twice the fuel, twice the light. But stars don't work that way. The relationship between mass and luminosity is far steeper than that. The real scaling law, the one that falls out of the physics, goes roughly as luminosity being proportional to mass raised to the power of 3.5, 3.5, which sounds like a dry bit of mathematics, and you don't need to carry that number with you, but what it means is extraordinary. A star twice the sun's mass doesn't shine twice as brightly. It shines about 11 times more brightly, just from being twice as massive. A star 10 times the sun's mass doesn't shine 10 times as brightly. It shines thousands of times more brightly, not hundreds, thousands. And if you go higher still, teach it to the truly enormous stars 30 or 40 or 60 times the sun's mass. You're talking about stars that blaze with a luminosity hundreds of thousands of times greater than our sun. They are visible from astonishing distances, beacons so fierce that they can sometimes be seen even in nearby galaxies. Great, extravagant, almost reckless things. You can actually see this law at work in the night sky, even though you probably never thought of it that way. When you look up and notice that some stars are much brighter than others, part of that difference is distance. Obviously, the closer ones look brighter. But some of that difference is real intrinsic power. The bright blue-white stars you might notice on a clear night, the ones that seem to sear slightly rather than just glow, many of them are simply more massive, burning with a ferocity that paler, quieter stars never approach. But here is where the story turns and where it becomes something almost morally weighted, something almost like a fable. The most massive stars, the most luminous ones, the great blazing giants, they don't live longest. They live shortest, by far. And the reason is precisely that lavish brightness. They are burning their fuel at a completely unsustainable rate, and the extra mass they started with doesn't save them. It barely delays the inevitable. Think of it this way. Imagine two people side by side, and you give the first person a somewhat larger pile of coins than the second. But then you also give the first person a spending habit so extravagant, so reckless, that they go through their coins at 10 times the rate. Who runs out first? The one with more money but a catastrophic rate of spending. That's a massive star. And the second person, careful and unhurried, stretching every coin? That's a small, dim red dwarf, barely above the ignition threshold. Mathematically, the lifespan scales in a way that is almost the mirror image of the luminosity. If luminosity goes up steeply with mass, lifespan tumbles steeply down. The relationship works out roughly as lifespan being proportional to mass divided by luminosity. And since luminosity rises so much faster than mass, the net result is that lifespan falls off steeply as mass increases. So let's put some numbers to it. Not because the numbers are the point, but because they are the only way to feel the full weight of what's happening.
A star about 60 times the mass of the Sun, one of those extravagant blazing O-type stars, will live for only a few million years. A few million? That sounds long when we're talking about human lives, but on the cosmic calendar, a few million years is almost nothing. It is a moment. It is a flash in the long, slow story of a galaxy. These stars are born, burn with extraordinary violence, and die before most of what we think of as Earth's interesting history has even begun.
Before the dinosaurs, before the first complex animals, before much of the fossil record we know, a massive star's entire life could fit inside the gap between one mass extinction and the next. Our Sun, with its far more modest mass, sits at around 10 billion years for its total main sequence lifespan. We're currently about 4.6 billion years in, roughly halfway. Plenty of time still left in the bank in cosmic terms, though we'll come back to why plenty of time is a somewhat misleading phrase, even for the Sun. And then there are the red dwarfs. Stars below about half the mass of the Sun, small and dim, burning such a frugal flame that their lifespans extend not to 10 billion years, not to 50 billion, but to trillions. A red dwarf at about a tenth of the Sun's mass might live for something like 10 trillion years. That's 1,000 times the current age of the universe. Let that breathe for a moment. The universe is roughly 13.8 billion years old. A 10th solar mass red dwarf has a main sequence lifespan of around 10 trillion years, give or take, which means the universe is still, in a very real sense, in the very early days of its own story. It's only a little over 1,000 years into a million-year novel, if red dwarf timescales are your reference point. Everything we call cosmic history, see the Big Bang, the first galaxies, every supernova ever seen, every civilization that has ever arisen anywhere, all of it has happened inside a tiny sliver of the time the universe has available. But the most striking thing about red dwarfs is not just how long they will live, it's what that lifespan tells us about the present moment. No red dwarf has ever died. Think about what that means. Every red dwarf that has ever formed, anywhere in the observable universe from the very beginning of star formation, is still burning. Not a single one has run out of fuel. Not one has reached old age. The universe is simply too young. We are still, right now, in a period where every red dwarf ever made is a living, burning star. They are all out there, every one, quietly fusing hydrogen at their unhurried pace, with trillions of years still ahead of them. Compared to that, the massive O-stars feel almost theatrical. They roar into existence, blaze so fiercely they illuminate whole regions of the galaxy and are gone in geological eye blinks, while the red dwarfs barely notice. And notice what this means for the galaxy as a whole. The initial mass function, the pattern that governs how many stars of each mass get born, is heavily weighted toward the small. The galaxy makes far more red dwarfs than anything else. Far more quiet, dim, patient stars than roaring monsters. In a sense, the galaxy is, by preference, modest. The great blazing stars are the exception, the punctuation. The red dwarfs are the vast majority, and they will outlast everything else by such an enormous margin that the final age of stars will be almost entirely their story, burning alone long after the more dramatic stars have all gone dark. But we're not quite there yet. Let's stay with a star in its prime, because once that ignition catches, once a young star has gathered enough mass to cross the fusion threshold and found its equilibrium, it enters the longest and most stable phase of its life. The phase astronomers call the main sequence. And the main sequence is in some ways a deeply comforting thing. Roughly 90% of a star's entire life is spent here. 90%. Everything that comes before the collapse from the cloud, the protostar phase, the long T Tauri period of Kelvin-Helmholtz contraction, is a prologue. Everything that comes after the swelling and the death and whatever comes beyond is an epilogue. The main sequence is the long middle of the story, the stable chapter. What makes it stable is something called hydrostatic equilibrium, and it is one of the most elegant self-regulating mechanisms in nature. Here is how it works. In the core of a star, gravity is always trying to pull everything inward. It has been trying since the very beginning of the collapse, but now there is fusion happening, and fusion releases energy, and that energy creates outward pressure, photons and particles pushing out against the weight of all that gas pressing in. The star reaches a balance point where those two forces exactly cancel each other out. Inward gravity, outward pressure. Perfect, sustained equilibrium. And what's remarkable is that this equilibrium is self-correcting. It's a thermostat. If the core gets a little hotter, say, if gravity compresses it slightly, then fusion rates go up, pressure goes up, the star puffs out a little, the core cools slightly, and rates come back down. If the core cools a little, the opposite happens. Gravity wins momentarily, compresses the core, heats it up. Fusion rates rise again, and pressure restores the balance. The star breathes, in a sense. It nudges itself back toward equilibrium over and over, all day, every day, for billions of years. This is why the main sequence lasts as long as it does, not because stars are just big and have a lot of fuel, though they are and they do, but because the fuel is being used at precisely the rate needed to hold everything in balance, no faster, no slower. The thermostat is always on. Now, the specific mechanism of hydrogen fusion varies depending on the star's mass, and the difference is worth knowing because it tells you something about how different stars really are beneath the surface. In a Sun-like star, but in all stars below about 1.3 solar masses, the dominant process is called the proton-proton chain. The name is fairly literal. Two protons, which are hydrogen nuclei, come together and begin a sequence of reactions that eventually produces a helium nucleus, releasing energy along the way. It's a straightforward process, if straightforward can mean anything about nuclear fusion. The proton-proton chain is not especially temperature sensitive. It runs at a steady pace across a fairly wide range of core temperatures. It is, in its way, the patient fusion mechanism. In more massive stars, those above about 1.3 solar masses, a different process dominates. It's called the CNO cycle, and the name comes from its catalysts: carbon, nitrogen, and oxygen. These three elements are used as a kind of intermediary in the fusion reactions, cycling through a sequence of reactions that begin and end with carbon, but ultimately fuse hydrogen into helium along the way. Crucially, the CNO cycle is far more temperature sensitive than the proton-proton chain. It responds to small changes in core temperature much more dramatically, which is part of why massive stars are so much more luminous and so much harder to keep in a gentle equilibrium. Their thermostat is more sensitive. They run hotter, brighter, and faster. Our Sun, for what it's worth, runs primarily on the proton-proton chain, a patient, steady burn, which is something of a relief. Let's stay with the Sun for a moment, because the numbers of what the Sun is doing right now at this very moment while you're listening are hard to fully absorb. They reward a slow look. Every second, the Sun is fusing roughly 600 million tons of hydrogen into helium, 600 million tons per second. That number is so large it doesn't really fit in the human mind, but it's not just large. There's something remarkable about what happens to all that matter. When 4 hydrogen nuclei fuse into one helium nucleus, the helium nucleus doesn't quite weigh as much as the 4 protons that went into making it. A tiny fraction of mass, a small but precise and real amount, simply vanishes. And where does it go? It goes in exact accordance with Einstein's equation, E equals mc squared, into energy. pure energy. The mass doesn't disappear, it converts. And because the speed of light squared is an enormous number, even a tiny amount of mass makes an enormous amount of energy. The Sun loses in this way about 4 million tons of mass per second, just turned into sunlight. 4 million tons every second, gone. The Sun is literally becoming lighter, moment by moment, day by day, year by year. And it has been doing this for 4.6 billion years. 4.6 billion years of losing 4 million tons per second. You can work out roughly how much mass the Sun has shed in its lifetime, and the answer is that it's a tiny fraction of its total mass, less than 0.1%, which is why the Sun still looks the same as it always has, and will for billions more years. But the number is not the point. The point is the sheer continuity of it, the absolute unflinching steadiness. Every second of every day for 4.5 billion years, the same reaction, the same conversion, the same patient burning. The Sun was doing this before life had crawled out of the sea on Earth. It was doing it before there was a sea. It was doing it before Earth existed at all. And it will keep doing it for roughly another 5 billion years. This one reaction at the center of an ordinary star sustained across timescales that reduced the entire span of human history to a rounding error. That's the main sequence. That's what it means to be in it. Now, you might have a question for me, if you're still with me. A very natural question. The Sun is making light constantly in its core. That light has to get out somehow. It has to travel from the center to the surface before it can fly off into space and eventually warm your face on a clear morning, or make the plants in a window reach toward the glass. How long does that take? The answer is one of the stranger facts in all of astrophysics, and it gives me genuine pleasure to share it with you. From the surface of the Sun to the Earth, a distance of about 150 million kilometers, light takes about 8 minutes. 8 minutes. That's the number most people know if they know any number about the Sun. The Sun is 8 light minutes away, comfortable, neighborly. But from the core of the Sun to its surface is a completely different story. The interior of the Sun is extraordinarily dense, not evenly dense, but dense enough in the radiative zone that a photon can barely travel any distance at all before bumping into another particle and bouncing off in a new direction. The photons produced in the core are constantly absorbed, re-emitted, scattered, absorbed again, scattered again, bouncing and ricocheting through this dense forest of particles in a process called photon diffusion. And because each collision sends them off in an essentially random new direction, they do not travel in a straight line outward. They random walk, 1 step forward, 2 steps sideways, half a step back, then sideways again. The result is that a photon, or really the energy of a photon, since photons get absorbed and re-emitted so many times they're really not the same photon throughout, takes somewhere between tens of thousands and 100,000 years or more to find its way from the core to the surface. The sunlight falling on your hands right now was born somewhere in that journey. The energy that produces it started somewhere in the core of the Sun tens of thousands of years ago, bouncing around in the dark interior long before modern humans had painted cave walls or built their first shelters. That energy wandered patiently and randomly through 100,000 years of collisions before finally reaching the surface and then making the 8-minute sprint to your window. That's the light outside. It's an old light, much older than you might think. And this thought leads somewhere interesting, because it means there's a kind of delay built into the Sun. What we see at the surface and the sunlight, the warmth, the energy we measure, it is not a real-time reading of the core's current state. It's a very old signal, a message from 100,000 years ago. If something changed in the Sun's core today, we wouldn't know it at the surface for a very long time. There's something almost meditative about that. The light you see is not the Sun as it is, It's the sun as it was. Now, I want to tell you something about the sun's future that surprises most people who hear it, because when we talk about the sun's eventual death, and we will get there in the next part of our journey tonight, people tend to assume that the drama is still comfortably far away, that we have billions of years before anything worrying happens. And in one sense, yes. The sun has roughly 5 billion years left on the main sequence before it begins the process of dying. But here's the thing, that's not quite the right deadline to worry about. The sun, like all main sequence stars, is not actually constant. It is very slowly, very gradually changing over its lifetime. Specifically, as hydrogen fuses into helium in the core, the composition of the core changes. Helium is denser than hydrogen for the same number of particles, and this causes the core to contract slightly over time, which causes the core temperature to rise slightly, which causes fusion rates to climb slightly. The net effect is that the sun is slowly getting brighter. Very slowly, but steadily. Right now, today, the sun is about 30% brighter than it was when it first ignited on the main sequence, 4.6 billion years ago. 30%. That's a lot when you think about what it means for a planet trying to maintain stable temperatures. And this creates what's called the faint young sun paradox, which is a genuine puzzle that planetary scientists have grappled with for a long time. Because if you run the physics backward, if you take the sun's luminosity 4 billion years ago and model what Earth's temperature should have been, the answer comes out too cold. Too cold for liquid water. Too cold for the early oceans that we know from geological evidence absolutely existed. Too cold for the first life. The early sun should have kept Earth frozen according to the simple model, but Earth wasn't frozen, life was already there. Something else must have kept the early Earth warm, probably a thicker atmosphere, more greenhouse gases, maybe other factors not yet fully understood. The faint young sun paradox is one of those puzzles that sits at the intersection of astronomy and geology and atmospheric science, unresolved in its details even now. But the flip side of that paradox is just as interesting, because if the sun was dimmer in the past and is brightening now, then the future sun will be brighter still, quite a bit brighter. And models suggest that in roughly 1 to 1.5 billion years, not 5 billion years, but 1 to 1.5 billion, the sun will be bright enough that the oceans of Earth will begin to evaporate. The planet will enter a runaway greenhouse process. The oceans won't just get warmer, they'll boil away, the water vapor will escape to space, Earth will dry out. And this will happen while the sun is still on the main sequence, still in the long, stable burning phase of its life, nowhere near dying. The sun won't even be approaching old age, 1 to 1.5 billion years from now, which sounds enormous. And it is enormous, of course, but it is almost nothing compared to the 5 billion years of main sequence life the sun has remaining. It's less than a quarter of the way through. The sun will be, by stellar standards, barely middle-aged when it becomes too bright for Earth. Now, 1 billion years is hard to feel. Human history, all of it writing and cities and empires and science, feels barely 10,000 years. 1 billion years is 100,000 times that. There is no reason to lie awake worrying about the sun's brightening in any immediate sense. But there's something worth holding on to here. This isn't just a frightening fact, it's actually one of the most remarkable things about main sequence stars. The very stability that makes them so long-lasting, the very equilibrium that lets them burn quietly for billions of years, comes with this slow, inexorable drift toward greater luminosity. The thermostat works beautifully, but it doesn't hold the output exactly constant. It drifts steadily in one direction. Over cosmic time, even the most stable thing changes. The sun burning steadily for 10 billion years is one of the great facts of our existence. We wouldn't be here without that stability. Life needs time, enormous amounts of time, to arise and evolve and develop the complexity to sit in a dark room listening to someone describe the death of stars. The main sequence gave us that time, but that same main sequence is, slowly, changing the conditions of the very planet where life used its time. There is something there that I find genuinely moving, if you'll let me say so quietly. The light that made us is also over enormous time, the light that will unmake the conditions that made us possible. Not as a cruelty, not even as a fact with a moral. Just as physics, the same law working steadily, beautifully, indifferently in all directions. Let's pause here just briefly and take stock of where we are. We started in a cold cloud at -260 degrees, slower even than liquid nitrogen, and we watched a clump of it collapse and spin and heat and accumulate until it crossed the threshold into true fusion. We met the brown dwarfs, the ones that almost made it. We saw how mass, just mass, that one number, determines not just whether a star ignites, but how brightly it burns and how long it lasts. We've met the extraordinary inverse. The more massive the star, the shorter its life. The most brilliant stars live and die, while the humblest red dwarfs barely stir. Every red dwarf ever born still burns. The universe is young enough that not one has died. We've spent time on the main sequence, the long stable equilibrium, 90% of a star's life held in balance between gravity and fusion, a thermostat running for billions of years. We've learned that our light is old, bouncing around inside the sun for 100,000 years before its 8-minute sprint to us. And we've learned that the sun's deadline for Earth isn't its death, it's its gradual brightening 1 billion or so years from now, which will end the ocean long before the star ends. And all of this, all of it, has been the prelude, the setup, the part of the story where our star is still young and burning and steady. Because the main sequence doesn't last forever. Eventually, every star that's burning hydrogen will burn its way through the hydrogen in its core. The fuel in the center, the specific region where the temperatures and densities are high enough to sustain fusion, will gradually be converted to helium. And when that happens, when the hydrogen in the core is gone, the thermostat fails. Not suddenly, not with a bang, not yet. But things begin to change, and the way they change is determined, again, by mass. By that one number, still doing its work, shaping everything that follows. We'll follow that into the next part of our journey, into the old age of stars, the swelling and the reddening, and the very different ways that different stars meet their endings. But for now, if you're still listening, and wherever you are, with whatever lamp is still on or window still pale, I hope you're feeling the weight of this one elegant idea, that a single number, mass, written at the moment of a star's birth, has already decided everything. Its brightness, its color, its lifespan, and its death. The life that follows from ignition is not a series of accidents. It is a consequence, a chain of physics following inescapably from that first gathering of matter out of the cold. Stars, in their way, are the most determined things in the universe, and the most mortal, each one carrying its own end in its very first breath. The next part of this journey, when we get there, will be darker and stranger and more beautiful. For now the stars are still burning, the red dwarfs in their trillions, the sun in its steady middle age, the great O-stars blazing briefly in the dark, all of them holding their equilibrium, all of them running their patient or impatient thermostat, all of them, in their different ways, still in the long, ordinary, extraordinary business of shining. That's what the main sequence is, the ordinary miracle of a star doing what it was always going to do. No rush. Rest here for a moment if you'd like. We'll find out what happens next when the fuel begins to run out. And so let's stay here just a little longer in that ordinary miracle, because there are things about the main sequence, about the long, patient burning, that are worth turning over slowly in the dark, like something you've been handed and haven't quite looked at closely enough yet. Let's talk about that one number in more detail, because it doesn't just sort stars into rough categories, it governs them with a precision that once you see it, feels almost unreasonable. The relationship between a star's mass and its luminosity, its brightness, follows what physicists call a power law. Specifically, luminosity scales roughly as mass to the power of 3.5, which sounds like an equation, and it is. But what it means in plain terms is this: double a star's mass, and you don't double its brightness. You multiply it by roughly 11. Take a star, 10 times the mass of the sun, and it burns not 10 times brighter, but something closer to 3,000 times brighter. The relationship is steep, almost punishingly steep. Bigger means not just brighter, but extravagantly, catastrophically brighter. And here is where the arithmetic turns against the giants, because a star's lifespan depends on how much fuel it has, divided by how fast it's burning that fuel. A more massive star does have more hydrogen, but it burns through that hydrogen so much faster because of the steep luminosity scaling that the net effect goes the wrong way. Lifespan scales roughly as mass to the power of -2.5. The bigger the star, the shorter the life, not slightly shorter, far shorter, catastrophically shorter. Take a star 60 times the mass of the sun, a true giant, an O-type star, blue, white, and brilliant, visible across thousands of light years. That star lives only a few million years, a few million. The sun, by comparison, lives around 10 billion years, and a red dwarf at 1/10 of the sun's mass lives not billions, but trillions of years, longer, by far, than the current age of the universe. Sit with that for a moment. A red dwarf born in the first few 100 million years after the Big Bang, one of the earliest stars to form, is still burning right now. Still there, still steady, still patiently fusing its hydrogen in the dark of some distant galaxy. It has barely begun. It has, in fact, so much time ahead of it that our entire civilization, our entire solar system, our entire sun's remaining life is barely a flicker in its biography. And more than that, no red dwarf has ever died, not one. In the 13.8 billion years since the universe began, not a single red dwarf has had time to exhaust its fuel and reach its ending. Every red dwarf ever born is still alive, still burning. Every single one. The universe is simply not old enough to have killed them. Whereas those brilliant O-stars, those blue giants burning 60 or 100 times the mass of the sun, they blazed and died before the solar system even formed, before Earth existed, before any of this. They poured their light into an empty cosmos, fused their fuel in a geological eye blink, and were gone. The most luminous things in the universe are the most temporary. The humblest, the most invisible, the most likely to be overlooked. Those will outlast everything. There is something in that worth carrying into sleep. Now, the sun. Our star, middling in every direction, neither giant nor dwarf, sitting quietly in the main sequence as it has for 4.6 billion years. What is it actually doing in there right now? The sun's core runs on what physicists call the proton-proton chain, a sequence of fusion reactions in which hydrogen nuclei, single protons, fuse together through a cascade of steps, eventually combining into helium. It is not a simple reaction. It requires conditions extreme enough that even in the core of the sun, at 15 million Kelvin and a density 150 times that of water, any given proton might wait billions of years before actually participating in a fusion reaction. The process is slow individually, but there are so many protons in such quantity that the collective rate adds up to something staggering. Every second, the Sun converts approximately 600 million tons of hydrogen into helium. 600 million tons per second. And of that 600 million tons, about 4 million tons simply disappear. Not into helium. Into pure energy via Einstein's equation, E equals mc squared, mass converted to light and heat and neutrinos with a completeness that nothing else in nature can match. 4 million tons of matter annihilated into energy every single second for 4.5 billion years, with roughly 5 billion more to go. The Sun is doing this right now as you lie wherever you are. A quiet, continuous destruction of matter on a scale that has no human comparison. And yet from here, it appears as a gentle warmth, a morning light through curtains, a bright patch in a blue sky. One of the things that helps with that perspective is knowing what happens to the light itself. It starts in the core. A gamma-ray photon is born in a fusion reaction deep inside the Sun at the very center. And then it begins its journey outward. That journey takes a very long time. The interior of the Sun is extraordinarily dense, so dense that a photon cannot travel more than a tiny fraction of a centimeter before being absorbed and re-emitted in a random direction. It doesn't stream outward, it wanders. A random walk, absorb and re-emit in no particular direction, bumping and scattering through layer after layer of plasma for tens of thousands of years. Some estimates run as high as 100,000 years or more, depending on where in the core the photon began its journey. Eventually, it reaches the surface, the photosphere, and there, for the first time, it can travel freely. 8 minutes later, it reaches you. The sunlight falling on your face this morning was born somewhere between 40,000 and 100,000 years ago, before the last ice age had ended, before the first humans painted caves in the quiet machinery of a star's core. It spent all that time wandering blindly through the dark interior, jostling through plasma, and then crossed 93 million miles of empty space in 8 minutes, as if the waiting had never happened. The light you see is ancient, the arrival is instant. And here is one more thing about the Sun before we move forward, because it matters, and it is strange, and it is closer than the red giants and the supernovae and everything dramatic that is still to come. The Sun has been gradually brightening across its lifetime. When it first ignited, roughly 4.6 billion years ago, it was about 30% less luminous than it is today, 30% dimmer, and it will continue brightening as it ages, as its core slowly contracts and heats, making the fusion reactions run a little faster, pushing the luminosity a little higher. This has a name, the faint young sun paradox, because the geological record shows liquid water on Earth from very early in its history, rivers, oceans, life, at a time when the Sun should have been too dim to keep water from freezing. Something, probably a thicker, early atmosphere rich in greenhouse gases, kept the early Earth warm enough, but that is a problem for another night. What matters here is the direction of travel. The Sun is getting brighter. And that brightening, which sounds pleasant enough in the abstract, has a deadline written into it. In roughly 1 to 1.5 billion years, long before the Sun runs out of hydrogen, long before it becomes a red giant, long before anything that would ordinarily count as the Sun dying, it will have brightened enough to push the Earth past a threshold. The oceans will begin to evaporate, the water vapor will trap more heat, a runaway greenhouse effect will take hold, and somewhere in there, the surface of the Earth will become uninhabitable, not dramatically, not in a flash, but completely. 1 to 1.5 billion years, The sun won't even be dying. It will still be in its ordinary middle age, still fusing hydrogen, still perfectly stable, just a little brighter than life on Earth can survive. So when someone says the sun has billions of years left, that is true. But Earth's window, the habitable window, it closes much sooner than the sun does. The star will outlive the planet's welcome by billions of years. That is the faint young sun paradox, turned around to face the future. And that is mass doing its quiet work again through time, shaping not just how a star burns, but what it does to everything around it, across timescales too long to really hold in the mind. You can only let them settle, let them sit somewhere behind the thoughts, the way a vast, calm thing should sit. So the sun burns on, slowly brightening, the planets turning around it in their quiet orbits. And for now, for the next several billion years, the thermostat holds. Hydrostatic equilibrium. That careful, ancient balance between the outward push of fusion and the inward pull of gravity. The sun in its long, unhurried middle age. But middle age, even for a star, does not last forever. There comes a point, not a dramatic moment, not a sudden event, more like a slow crossing of a line, when the fuel in the core runs low, when the hydrogen at the very center of the sun has been fused and fused, proton by proton, chain by chain, for so many billions of years that there simply isn't enough left to keep the fire going the way it once did. The core begins to run out. And this is where the story changes, not with a bang, not yet. With something quieter and in some ways stranger. A shift in the balance that the sun has maintained for almost its entire life. Picture the core of the sun as it is now, a dense, searingly hot region at the heart of the star where the proton-proton chain ticks along, converting hydrogen to helium, releasing energy, pushing outward, holding gravity at bay. That process has been the sun's whole identity for the last 4.5 billion years. It is what the sun is, a hydrogen-burning star, a main sequence star. But helium doesn't fuse easily, not at the temperatures the sun currently maintains. And as the core fills with more and more of it, helium being the ash, the leftover product of all that hydrogen burning, the core begins to change character. The fuel thins, the reactions slow, the outward push weakens just slightly, but enough. Gravity notices, and gravity, as we have said before, is patient. It has been waiting since before the sun was born, held off only by the pressure of fusion. The moment that pressure falters, gravity presses in. The core begins to contract, to squeeze tighter, to get smaller and denser, the way things do when nothing is holding them up anymore. Now here is the part that catches people off guard. You might expect the whole star to contract at this point. Core collapses, star shrinks, everything gets smaller. And that would make a certain intuitive sense. But that is not what happens. What happens is almost the opposite. And it happens because of a quirk in how heat and pressure distribute themselves through a star's layers. As the helium core contracts, it heats up. The compression squeezes energy into a smaller space, and that heat spreads outward into the surrounding layers, the layers just outside the core that still contain hydrogen. Those layers, warmed by the contracting core below them, become hot enough to start fusing on their own. A shell of hydrogen ignition forms around the inert helium core, a ring of fire burning at a layer where burning was never happening before. And this shell burns intensely, more intensely in some ways than the core ever did. The energy it produces is enormous. It floods outward through the star's outer layers with a pressure that the star's structure cannot easily accommodate. So the outer layers expand, not by a little, by an almost unimaginable amount. The star swells. The outer envelope, the part of the star we can see, the photosphere, the surface, pushes outward and outward, growing larger, getting more diffuse. And as it expands, as that envelope thins and spreads across a much greater volume, something happens to its temperature. It cools. A gas spread thin is a gas that isn't holding its heat as tightly. The surface drops in temperature from the roughly 5,500 degrees Celsius the Sun shows today, down toward 3,000 or 4,000 degrees. And cooler objects glow differently. Cooler objects glow red. The Sun becomes a red giant. It is worth staying with that for a moment, because the phrase is used so casually in textbooks and documentaries that it can slide past without really landing. Red giant. It sounds like a category, a label, a box to tick in the stellar life cycle. But it is an event of truly staggering physical scale. The Sun today has a radius of about 700,000 kilometers. The Earth, by comparison, is about 150 million kilometers away from the Sun. Right now, that distance feels vast. The Sun is a bright point from where we stand, a disk in the sky, something you can cover with your thumb if you hold it up at arm's length. It fits comfortably in the imagination. When the Sun becomes a red giant, it will swell to a radius roughly equal to the current orbit of the Earth, maybe slightly beyond it. It will grow to engulf Mercury, that small, scorched, cratered world closest to the Sun. It will swallow Venus, that cloud-wrapped planet we once imagined might be habitable. And the Earth itself, depending on how the physics works out, may or may not be engulfed. The estimates vary. Some models suggest the Earth's orbit will shift outward as the Sun loses mass, keeping it just ahead of the expanding surface. Others suggest it will be absorbed. Either way, it will not be a pleasant place to be. The Sun, our Sun, the star that built the warmth that built life, will become a thing of planetary scale. A red, swollen, luminous enormity filling the sky, or what would be the sky if there were anything left to see it. This will happen in roughly 5 billion years. Not soon, not something to lose sleep over tonight, but it is the direction the Sun is already traveling, has always been traveling. The path was set when the mass of the cloud that formed it was decided, because mass set the timeline, mass set the fuel supply, mass set the rate of burning, and mass is now setting the manner of the Sun's old age. But we have not arrived at the end yet. The red giant phase is not the finale. It is more like the beginning of the last act, because something else is happening inside. All this time, the outer layers are swelling. The helium core, no longer held up by hydrogen fusion, is contracting and heating, getting denser, getting hotter, squeezing down toward a new threshold. A threshold that requires much higher temperatures than hydrogen fusion. Because helium nuclei are heavier than hydrogen nuclei, they carry more positive charge, and that means the electrostatic repulsion between them, the force that pushes same charge particles apart, is stronger. You need more energy, more speed, more temperature to push helium nuclei close enough together for the strong nuclear force to take hold and bind them. How much more temperature? About 10 times more. The Sun's core today, where hydrogen fuses, sits at roughly 15 million degrees Celsius. For helium to fuse, you need somewhere around 100 million degrees Celsius, nearly 10 times hotter than the current core. That is not a small step. That is a threshold the core has to claw its way toward, degree by degree, as the contraction squeezes harder and harder. In a more massive star, a star several times the mass of the Sun, the core reaches helium ignition temperature gradually in a relatively smooth and continuous way. Helium fusion switches on almost like hydrogen fusion switched on at ignition, with a kind of slow building pressure. But the Sun is not that massive. In a star like the Sun, the helium core, as it contracts, reaches a strange state before it ever gets hot enough to fuse. The electrons inside it, those tiny particles orbiting the helium nuclei, get packed so closely together that quantum mechanics steps in and changes the rules. This is electron degeneracy pressure. the same quantum effect that will eventually support the Sun's remnant core as a white dwarf. The Pauli exclusion principle, a law of quantum mechanics that says no two electrons can occupy the same quantum state at the same time, means that as electrons are squeezed together, they resist. Not because they're hot, not because they're moving fast in the thermal sense, but because the laws of quantum physics simply do not allow them to be pushed into identical states. They push back. The pressure they exert is not thermal pressure. It doesn't follow the usual rules. It is a kind of quantum stiffness. And in a degenerate core, temperature and pressure are decoupled. Normally, in a gas, if you heat it up, the pressure rises and the gas expands and cools down again, a natural thermostat. But in a degenerate gas, heating it doesn't increase the pressure in the same way. The pressure is set by the density, not the temperature. So the thermostat is broken. This matters enormously for what happens next. When the degenerate helium core of the Sun finally reaches 100 million degrees, helium fusion ignites. But because the pressure doesn't rise with the temperature, because the thermostat is broken, the ignition doesn't moderate itself. The fusion produces heat, the heat causes more fusion, which produces more heat, which causes more fusion, in a runaway chain that takes only seconds to flash through the entire core. This event has a name, the helium flash. It is one of the more dramatic moments in the life of a sun-like star. In a matter of seconds, the helium core releases an enormous burst of energy. Not an explosion in the dramatic, visible sense. The energy is absorbed by the outer layers of the star before it reaches the surface. From the outside, you would see only subtle changes. But inside, in the core of the star, there is for a few seconds an energy release comparable to the output of the entire Milky Way galaxy, 1 trillion suns burning for a few seconds inside the heart of our Sun. And then the degeneracy is lifted. The temperature rise finally brings the core out of the degenerate state. The thermostat comes back on. Helium fusion stabilizes. The star settles into a new equilibrium, fusing helium in the core instead of hydrogen, and the outer layers contract a little, and the star enters what astronomers call the horizontal branch, a new, stable phase, quieter than the helium flash that started it, burning helium steadily in the core while hydrogen continues to fuse in a shell around it. The Sun has a second life, shorter than the first, but real. And in this second phase, something extraordinary is being made. Helium fusion, unlike hydrogen fusion, doesn't produce another simple light element. It produces something heavier. When 3 helium nuclei come together in the right sequence, in a process called the triple alpha process, 3 alpha particles, 3 helium nuclei, they produce carbon, the element on which all known life is built. Every protein, every DNA strand, every cell membrane in every living thing on Earth. Carbon. It is being forged right now in the cores of aging stars all across the galaxy. Stars heavier than the Sun in their main sequence phase. Stars like the Sun in their red giant phase, fusing helium into carbon via the triple alpha process. The universe is full of stellar cores doing exactly this quietly, in the dark, for billions of years at a time. But here is the thing about carbon that should stop you. The triple alpha process is extraordinarily improbable. Getting 3 helium nuclei to come together at the right place and the right time, in the right order, is something that should almost never happen. The intermediate step, 2 helium nuclei fusing to form beryllium-8, is also deeply unstable. Beryllium-8 falls apart in about 10 to the -17 seconds, an almost unimaginably brief window. For carbon to form, a 3rd helium nucleus has to arrive and fuse with that beryllium before it disintegrates. The mathematics of this, worked out in the mid-20th century, suggested that carbon should be almost impossibly rare. The reaction should be far too slow, far too unlikely to produce the abundance of carbon we actually see in the universe. There was a gap between what the physics predicted and what the universe clearly contained. And then Fred Hoyle looked at the problem from the other end. Hoyle, a British astrophysicist, deeply contrarian, one of the great scientific minds of the 20th century, argued that because carbon exists in abundance, because we are made of it, because life is built from it, the physics must allow it. There must be something that makes the triple alpha process efficient enough. And he predicted, before any measurement confirmed it, that carbon-12 must have a specific energy resonance, a specific quantum energy state at almost exactly the right level that allows the beryllium-8 and the third helium nucleus to combine efficiently before the beryllium falls apart. This resonance is called the Hoyle state, and when physicists went and looked for it in the laboratory, they found it, exactly where Hoyle predicted, at almost precisely the right energy. The match between prediction and measurement was so close that it remains one of the most striking examples of reasoning backward from our own existence to a conclusion about physics. If the Hoyle state were even slightly different in energy, slightly higher or slightly lower, carbon would not form in stars, and without carbon, chemistry, as we know it, collapses. Life as we know it becomes impossible. The universe is calibrated at the nuclear level to make carbon, and Hoyle saw that from first principles. We exist, therefore carbon exists, therefore the resonance must be there.
Let that settle for a moment. The carbon in your body, every atom of it, passed through the interior of a red giant star, forged by a process that works only because of a quantum resonance that had to be almost exactly right. And we know it had to be exactly right because you are here to notice it.
There is a quietness to that underneath the strangeness, a sense that the universe has been making you at the atomic level for a very long time. Before the Earth existed, before the solar system existed, in the cores of stars that lived and died long before our sun was born. But we are getting a little ahead of ourselves. The sun, in its red giant phase, fuses helium to carbon. And then, because the same story plays out again, the core exhausting its fuel, the ash of one reaction becoming the material of the next. The helium in the core runs out as well. For a star, the mass of the sun, this is where the fusion story ends. The sun does not have enough mass to push the core to the temperatures needed to fuse carbon. Not even close. Carbon fusion requires temperatures on the order of 500 to 600 million degrees, 6 times hotter than helium ignition. The sun's core, even after helium burning, will not get there. So the core sits filled with carbon and oxygen. Oxygen forms alongside carbon in the triple alpha and related processes, and it contracts again, but this time the contraction is the final contraction. There is no next fuel waiting, no new threshold to cross. Gravity presses in and the electron degeneracy pressure builds, and the core settles into a state from which it will never rise again. What is left at the core of the dying sun is a white dwarf. But we are not done with the outer story yet, because as the sun's core collapses into that final degenerate state, what happens to the enormous swollen outer envelope, all that gas that expanded when the star became a red giant? It doesn't stay put. It doesn't simply fall inward with the core. In the final stages of a sun-like star's life, a phase called the asymptotic giant branch, where the star grows even larger and more luminous than it was as a red giant, pulsing and swelling on the thin fuel in its outer shells. The outer layers are loosely bound. The gravity holding them to the core is relatively weak because the core is tiny and the envelope is so far out, so spread thin. And the radiation pressure from the luminous core below pushes them outward. A stellar wind, This wind strengthens as the star ages. The outer layers begin to drift away, not violently, not in an explosion, more like a slow exhalation. The outer envelope of the star, which was once the sun's atmosphere and corona and outer layers, simply leaves, drifts outward into space over thousands of years, forms a shell of gas expanding away from the remnant core. And as this happens, the hot core underneath is gradually exposed. At first, it's hidden behind the layers. Then, as the layers thin and move outward, the core's intense ultraviolet radiation reaches the drifting gas and ionizes it, strips electrons from the atoms, making the gas glow. Luminous shells of glowing gas lit from within by the exposed remnant core. This is a planetary nebula. The name is a misnomer, as it happens. A beautiful one, but a misnomer. These have nothing to do with planets. The name was given by William Herschel, the 18th century astronomer who also discovered Uranus, because when he looked at them through his telescope, their round, disc-like appearance reminded him of the discs of planets. They looked planet-like, so he called them planetary nebulae, and the name stuck long after the actual nature of these objects was understood. What they actually are is something far stranger and more beautiful. The last breath of a dying sun-like star. Glowing clouds of carbon, oxygen, nitrogen, the elements the star spent its life making, expanding slowly outward into the interstellar medium, lit by the exposed core within. They glow in extraordinary colors, the turquoise and blue of ionized oxygen, the red of hydrogen, the green of doubly ionized oxygen, depending on the composition and density of the gas. When you see photographs of them, the Ring Nebula, the Helix Nebula, the Cat's Eye Nebula, you are looking at the expelled outer layers of dead sun-like stars, billions of years of stellar life unwinding into space in a final, slow, luminous exhale. And at the center of each planetary nebula, the remnant, the white dwarf. This is what the sun will become, not in fire and fury, not in the devastating explosion that some stars meet. The sun will shed its outer layers, breathe them out into a glowing cloud, and leave behind at its heart a white dwarf, a remnant, the compressed, hot, inert core of the star that was. How dense is a white dwarf? This is one of those places where the numbers require a moment to absorb, because they don't behave the way numbers usually behave in everyday life. A white dwarf contains roughly the mass of the Sun, all of it or close to it, packed into a volume roughly the size of the Earth. Not similar to the Earth in some vague poetic sense. Actually, about the volume of the Earth. Our Sun, 1.4 million kilometers across, squeezed to something 12,000 kilometers wide. A teaspoon of white dwarf material would weigh about a ton, not a metaphorical ton, an actual ton. If you could somehow lift a teaspoon of white dwarf matter, which you cannot for many reasons, it would weigh as much as a small car per teaspoon. This density is not the result of the atoms being crushed out of existence. The atoms are still there, the nuclei, the electrons, but they have been packed far closer than they are in ordinary matter. In everyday matter, in you, in this air, in a rock. Atoms are mostly empty space. The nucleus at the center is tiny compared to the electron cloud around it. Crush that space away, pack the electrons as close as physics allows, and you get something approaching white dwarf density. But here is the crucial thing. The white dwarf is not fusing. It is not producing energy. The nuclear fire is out, so what is holding it up? What is stopping gravity from squeezing it further? What stops a white dwarf from simply collapsing into something even smaller and denser? The answer is electron degeneracy pressure. The same quantum effect that triggered the helium flash is now the only thing holding the white dwarf together. the Pauli exclusion principle. No two electrons can be in the same quantum state at the same time. As the electrons are packed closer and closer, they resist, not because they're hot, not because they're moving due to thermal energy, but because quantum mechanics forbids them from occupying the same state. They push back, they hold the structure up. This is a quantum force. It has nothing to do with temperature. A white dwarf could cool to absolute zero still if you waited long enough, which we will come back to, and the electron degeneracy pressure would remain. It is not a pressure that depends on heat. It is a pressure that depends only on density and the laws of quantum mechanics. And so a white dwarf simply sits, slowly cooling, radiating away the heat it accumulated over billions of years of stellar life. Over millions, billions, trillions of years, it will cool and dim, shifting from white to yellow to orange to red, its light slowly fading, growing cooler and dimmer and darker, until eventually, if you wait long enough, it would become what physicists call a black dwarf, a cold, dark, inert sphere of dense carbon and oxygen, no longer glowing, no longer visible, just floating in space in the dark. But here is something remarkable. No black dwarf has ever been observed, not one, not anywhere in the observable universe, and this is not because we haven't looked hard enough. It is because the universe is not old enough to have made one. The time required for a white dwarf to cool to the point where it would qualify as a black dwarf is estimated to be somewhere on the order of a quadrillion years. 10 to the power of 15 years. The current age of the universe is about 13.8 billion years, 1.38 times 10 to the 10th. We are not even close to the timescale on which black dwarfs become possible. Every white dwarf that exists today, and there are many scattered through the galaxy, the remnants of stars that lived and died over billions of years, is still warm. Still glowing, at least faintly. None of them have had time to go dark. The black dwarf is a prediction, a fate that the universe has written in its physics but has not yet had time to deliver. A future object that will exist only in a universe that has aged to timescales we can barely name, long after the sun has become a white dwarf. Long after that white dwarf has cooled and dimmed. Long after most of the stars currently alive have finished their own lives and left their own remnants. In a cold, dark future universe, there will be black dwarfs drifting through the dark. But that is so far away as to be almost another universe entirely. What matters now for the sun's story is this. The sun will become a white dwarf. Its mass, about 1 solar mass, places it clearly below the threshold that would lead it anywhere else. It will shed its outer layers, form a planetary nebula, and leave a white dwarf behind, and that white dwarf will cool slowly across timescales that dwarf even the sun's main sequence life. But, and this is important because it is where mass writes the plot, the white dwarf fate is not available to all stars. There is a limit. In 1930, a young Indian physicist named Subrahmanyan Chandrasekhar was on a steamship voyage from India to England, traveling to take up a position in Cambridge. He was 19 years old. And on that voyage, with nothing but time and a notebook and the equations of quantum mechanics and general relativity, he worked out something that would eventually reshape our understanding of what stars can become. He calculated the maximum mass that a white dwarf can have. The electron degeneracy pressure that holds a white dwarf up is powerful, but it is not unlimited. As you add more mass to a white dwarf, as you pile on more material, squeeze more matter in, the electrons have to move faster and faster to maintain the quantum pressure. Up to a point, they can. But as the electrons approach the speed of light, relativistic effects start to change the mathematics. The pressure they exert doesn't increase as fast as the gravity trying to crush inward. There is a point beyond which even electron degeneracy pressure cannot hold. Chandrasekhar worked out where that point is. His calculation placed the limit at about 1.4 times the mass of the Sun. A white dwarf more massive than 1.4 solar masses cannot be supported by electron degeneracy pressure. It will collapse further. This is the Chandrasekhar limit, 1.4 solar masses. And it is one of those numbers in physics, like the speed of light, like Planck's constant, that shows up everywhere once you know to look for it. It is the dividing line between one kind of stellar death and another. A white dwarf below 1.4 solar masses sits comfortably in its quantum equilibrium. A core that somehow exceeds 1.4 solar masses cannot rest as a white dwarf. Something more violent must happen. When Chandrasekhar first proposed this limit, the astrophysical establishment was not welcoming. Arthur Eddington, one of the most respected astronomers of the era, and the same man who confirmed Einstein's general relativity during the 1919 solar eclipse, publicly dismissed Chandrasekhar's result. He found it philosophically unacceptable, the idea that there could be things that could not become white dwarfs, that had no stable state to rest in. Eddington mocked the result. The idea of a star that simply could not stop collapsing seemed, to him, absurd. But the mathematics was right. Chandrasekhar was right. He was awarded the Nobel Prize in Physics eventually in 1983, more than 50 years after that steamship calculation. And the physics he worked out on that voyage is what tells us everything about how the story branches. A star like the Sun produces a core that ends up, after shedding its envelope, well below 1.4 solar masses. The white dwarf the Sun leaves behind will be maybe 0.5 or 0.6 solar masses, comfortably within the Chandrasekhar limit. The electron degeneracy pressure holds, the remnant is stable, but not all stars end there, not even close. Above a certain initial mass, or within above roughly 8 solar masses, the story is entirely different. The physics branches at 8 solar masses. Below it, white dwarf. Above it, something far more violent. Something that begins with iron. And that is where we are going next. But before we leave the white dwarf, let's stay with it just a moment longer, because there is something worth carrying forward, something that connects the white dwarf not just to the physics, but to the broader story this whole night has been about. The Sun will die quietly. By stellar standards, almost elegantly. It will not explode, it will not collapse into a black hole, it will not send shockwaves across the galaxy. It will swell, breathe out its outer layers, glow briefly in the glorious colors of a planetary nebula, and leave a white dwarf at its heart. A dense, cooling sphere supported by quantum pressure, slowly giving back the heat it accumulated over 10 billion years of fusion. This is something worth saying plainly because there is a persistent idea in popular culture that the Sun will explode, that it will go supernova, that one day the Sun will detonate and take the inner solar system with it in a cataclysm of stellar violence. It will not. The Sun is too small, too modest in its mass. A supernova requires something much heavier. We will get to exactly how much heavier in a moment because the number matters. The Sun's mass, fixed at birth, rules out the supernova entirely. It rules out the neutron star. It rules out the black hole. It writes, in the physics of nuclear thresholds and degeneracy pressure and the Chandrasekhar limit, a quieter fate. And in that quieter fate, there is something worth recognizing. The Sun has spent billions of years fusing hydrogen to helium, and in its last gasping phases fusing helium to carbon and oxygen. Those elements, the carbon and oxygen, in the core of the white dwarf the Sun will become, and the carbon and oxygen in the planetary nebula drifting outward, those elements will eventually mix into the interstellar medium, into the gas and dust clouds of the galaxy. And from those clouds, eventually, new stars will form, new solar systems, new planets, and perhaps new life built on carbon atoms forged in the sun's core billions of years before. The sun will die, but what it made will not. So there are, at this point, 2 of our 4 thresholds named. The 0.08 solar mass threshold, the ignition line, the dividing point between a true star and a brown dwarf, and the 1.4 solar mass threshold, the Chandrasekhar limit, the dividing line between a peaceful white dwarf and something that must collapse further. We have accounted for the lowest mass stars, the red dwarfs that burn so slowly they will outlive the current universe by trillions of years. And we have accounted for the sun-like stars, the ones above 0.08 but below the threshold where things get catastrophically violent, which end as white dwarfs after a patient, beautiful, ultimately quiet death. But the story of mass is not finished, not by a long way, because above a certain line, and above roughly 8 solar masses, where the thermostat doesn't just switch off, it fails catastrophically. The core doesn't just cool and collapse, it collapses violently in under a second, releasing in that fraction of a moment more energy than the sun will produce in its entire 10 billion year life. And from that violence, 2 more kinds of object emerge, depending on one more threshold, one more number, waiting in the physics like a final gate. The threshold between a neutron star and a black hole. But that story begins with iron, and we will get to iron. Its role in this is unlike anything else in the periodic table. It is the element that kills massive stars, not by accident, not by coincidence, but by a deep and inescapable logic in the physics of nuclear binding energy. Iron is where the energy story of fusion ends. And when the core of a massive star fills with iron, the result is one of the most violent events the universe produces. Before we get there, though, let's take one more quiet breath with the white dwarf. There is a thought I want to leave with you before the violence begins. The white dwarf is, in a sense, the most common stellar remnant in the galaxy. Most stars, the vast majority of stars by number, given how heavily the initial mass function favors small masses, are low enough in mass that they will eventually end as white dwarfs. The sun will. Billions of other stars will. And those white dwarfs, once formed, are extraordinarily stable. They do not decay. They do not undergo further fusion. They do not transform into something else except over timescales that dwarf the current age of the universe. They are, in a strange way, among the most enduring objects the universe makes. A white dwarf formed in the first billion years of the universe is still out there, still cooling, still present, still supported by the Pauli exclusion principle and the quantum refusal of electrons to share a state, still floating in the dark, giving off the last of the heat it absorbed over its stellar life, a relic, a quiet witness to a universe that was very young when it was born. There is something in that, something that invites a kind of stillness if you let it. The star burned for billions of years, and the remnant of it will persist for billions more, slowly cooling, slowly fading, not gone, not destroyed, changed, compressed, carrying in its carbon-oxygen heart the record of everything it fused, everything it made, everything it burned over the long course of its life. Mass set this fate. At the moment of formation, in the cold, dark, collapsing cloud where the sun began. The mass of that cloud, the mass of the protostar that emerged, the mass written into the equations of hydrostatic equilibrium and the Chandrasekhar limit and the triple alpha process, all of it pointed here, to a white dwarf, to a planetary nebula, to carbon drifting back into the galaxy to become, someday, something else. One number, one fate. And now the other fates, the ones that begin above 8 solar masses, the ones that involve iron. Let's go there slowly. A massive star, say a star of 10 solar masses or 20 or 60, lives its main sequenced life very differently from the Sun. We have touched on this already in the earlier part of our journey tonight. The luminosity-mass relationship is brutal. A star 10 times the Sun's mass is not 10 times as bright, but thousands of times brighter. It burns through its hydrogen supply at a correspondingly ferocious rate. What takes the Sun 10 billion years on the main sequence takes a 10 solar mass star tens of millions of years. What takes the Sun 10 billion years takes a 60 solar mass star only a few million, fast, bright, profligate. But the manner of death and how the actual sequence of events in the core of a dying massive star begins the same way the Sun's begins. The core hydrogen runs out, the core contracts, a hydrogen shell ignites, the outer layers swell. The massive star becomes a red supergiant rather than a red giant, a distinction of scale that is almost impossible to adequately convey. The largest red supergiants are so enormous that if placed where the Sun is, they would extend beyond the orbit of Jupiter. The Sun's red giant will reach Earth's orbit. A red supergiant dwarfs even that. But this outer story, the swelling, the cooling, the reddening, is not where the important action is for a massive star. The important action is happening in the core. Because a massive star has enough mass, enough gravitational pressure to push the core to temperatures the Sun will never reach. Carbon fusion, impossible for the Sun, is reached in the cores of massive stars as a matter of course. At several 100 million degrees, carbon begins to fuse. Carbon fusion produces neon, magnesium, sodium. The core fills with the products of carbon fusion. The carbon runs out. The core contracts again, heats again. The next threshold is reached, neon fusion, then oxygen fusion, then silicon fusion. Each step requires higher temperatures than the last, and each step is faster than the last, much faster. The Sun spent billions of years fusing hydrogen. In a massive star, carbon fusion takes hundreds to thousands of years. Neon fusion takes about a year. Oxygen fusion takes months. Silicon fusion, in the final step, takes about a day. A day. From the outside, you would see nothing. The star would look like a red supergiant, enormous and luminous, pouring light and stellar wind into the surrounding space. The internal drama of these final fusion stages is invisible. The energy they generate is swallowed by the star's outer layers, but inside the core is building towards something that cannot be sustained. Each layer of fusion is happening simultaneously in nested shells around the center, hydrogen fusing in an outer shell, helium fusing in the next shell inward, carbon, neon, oxygen, silicon, each in their own shell, each burning at a different temperature, nested like the layers of an onion made of stellar fire. At the very center of this onion, the silicon shell is producing iron. And this is where everything changes. Iron is the most stable nucleus in the periodic table. Not the heaviest, there are many nuclei heavier than iron, but the most stable in a specific thermodynamic sense. The binding energy per nucleon, the energy that holds each proton and neutron inside the nucleus, is highest for iron 56. It is, in the language of nuclear physics, the valley of the energy landscape. The bottom of a hill. Every fusion reaction up to iron releases energy, because moving toward iron from below means releasing the energy tied up in the nuclear binding. Hydrogen fusing to helium, energy released. Helium to carbon, energy released. Carbon to neon, neon to oxygen, oxygen to silicon, silicon to iron. Each step, energy released. That released energy is what the star has been living on for its entire life. That is the light. That is the heat. That is the outward pressure that has been holding gravity at bay for millions of years. But iron fusion absorbs energy. Moving past iron, trying to fuse iron into something heavier, doesn't release energy. It costs energy. The valley goes uphill on both sides. Iron is the bottom. So when the silicon in the core finishes fusing, in about a day, remember, what is left is an iron core, a growing inert ball of iron at the heart of the star, an iron core that cannot fuse, that produces no energy, that provides no outward pressure. That simply sits there, growing heavier as the silicon shell above it continues to produce iron and dump it onto the core. And gravity is patient. The iron core grows. It grows toward the Chandrasekhar limit, that same 1.4 solar masses that limits white dwarfs. As it approaches the limit, the electron degeneracy pressure that is holding it up begins to feel the strain. But unlike a white dwarf, the iron core is not static. It is growing, being fed from above. It cannot simply cool and wait. The pressure is building. When the iron core reaches about 1.4 solar masses, when it crosses the Chandrasekhar limit, the electron degeneracy pressure gives way. And then the core collapses. Not slowly, not gradually, in a fraction of a second. In less than 1 second, the iron core of a massive star, which was approximately the size of the Earth, collapses to a sphere about 20 kilometers across, from Earth-sized to city-sized, in under a second, at speeds approaching 25% of the speed of light. And from that collapse, everything else follows. But that is the next part of the story, and we will get to it. The collapse, the rebound, the catastrophic explosion, the objects it leaves behind. The two remaining thresholds, the ones that separate a neutron star from a black hole, the ones that produce pulsars spinning 700 times per second, and objects from which not even light escapes. We will get there. For now, let the collapse hang in the air for a moment. The iron core. The silence before it gives way. The patient pressure of gravity, held off for millions of years by fusion, finally crossing a line that cannot be uncrossed. The star has been burning since before the Earth was formed. It has fused hydrogen, then helium, then carbon, and neon, and oxygen, and silicon, each step faster than the last, each step feeding an iron core that cannot burn. And now the core has reached the limit that Chandrasekhar calculated on a steamship voyage, at 19 years old, crossing the ocean. The limit beyond which electron degeneracy pressure cannot hold. Gravity is pressing in. And in less than a second, everything changes. The collapse begins. Not with a sound, not with a flash of light. For a fraction of a second, the iron core of a massive star, a core that has been building patiently, layer by layer, through millions of years of escalating fusion, simply falls inward. The thing that was approximately Earth-sized becomes, in less time than it takes to blink, a sphere about 20 kilometers across. The density that results is almost impossible to hold in the mind. Every proton and electron in that core is jammed together so forcefully that they merge, the electrons and protons combining to become neutrons, releasing a vast flood of neutrinos as they do, and the core transforms into something that has never existed anywhere in the universe until this moment, a neutron star. But the outer layers of the star don't know this yet. They are still falling. They were already on their way in, riding the gravitational collapse, falling faster and faster toward where the iron core used to be. And now they hit. They hit the newborn neutron star, which is almost incompressibly hard, supported not by heat, not by fusion pressure, but by neutron degeneracy pressure, the same quantum stubbornness that holds white dwarfs together, except operating at a much smaller scale and a much more extreme density. The neutron star refuses to compress further. The infalling outer layers slam into it and rebound. A shock wave explodes outward through the star, and the star tears itself apart. This is a core collapse supernova, a Type II supernova. And the scale of it is one of those facts that, even after you've heard it several times, still does something quiet and strange to the part of you that tries to understand size. A single supernova can briefly outshine its entire host galaxy. Not a few bright stars, not a cluster or a nebula. The entire galaxy, hundreds of billions of stars, all burning at once, can be outshone by a single star in its final moments. For days, sometimes weeks, one dying star blazes with the light of hundreds of billions. Astronomers across history have recorded them appearing suddenly in the sky, new stars in places where no star was visible before. The word nova comes from the Latin for new, a new star appearing as if from nothing. Except it isn't new, it's very, very old. It's saying goodbye. And here is the detail that quietly rewires something in you if you let it. Of all that staggering energy and the explosion that outshines a galaxy, the shock wave that tears a star to pieces, roughly 99% of it doesn't come out as light at all. 99% of the energy released in a core collapse supernova escapes as neutrinos, invisible, nearly massless, passing through everything. In the seconds of the collapse, the newborn neutron star emits more energy in neutrinos than the Sun will emit in its entire 10 billion year life. It does this quietly, invisibly, in a burst that lasts about 10 seconds. The brilliant flash of light that astronomers see that outshines a galaxy, that is the leftover 1%. The universe does most of its loudest work in silence. So there it is, the second death, the death of a star more than about 8 times the mass of the Sun. It builds an iron core. The iron core reaches the Chandrasekhar limit. Electron degeneracy pressure gives way. The core collapses to 20 kilometers across in under a second. The outer layers rebound off the newborn neutron star. A supernova explodes, and the neutron star is left behind, sitting at the center of an expanding cloud of glowing gas and shattered stellar material. Let's stay with the neutron star for a moment because it deserves a moment. A neutron star is approximately 20 kilometers wide, about the size of a city. Manhattan, end to end, gives you roughly the diameter, and into that city-sized sphere is packed roughly 1.4 times the mass of the Sun, which is about 1,000,000 times the volume of the Earth. 1.4 of those pressed into something you could fly across in a small aircraft. The density of a neutron star is close to the density of an atomic nucleus. It's the core of an atom, stripped of all the empty space that normally makes up most of matter. Ordinary matter is almost entirely empty. If you took all the empty space out of every human body on Earth, the whole of humanity would fit into something about the size of a sugar cube. Neutron stars have done something like that at a stellar scale. A sugar cube of neutron star material, just that small white cube you might drop into a cup of tea, would weigh approximately as much as all of humanity combined, about 1 billion tons in a volume the size of your thumbnail. Take a second with that if you'd like. There's no rush. 1 billion tons in a sugar cube. And neutron stars are not exceptions or oddities. They are a normal product of normal stellar death, scattered across the galaxy by the thousands. What holds a neutron star up? The same thing that holds a white dwarf up, in principle, degeneracy pressure. But now it is not electrons that are squeezed to their quantum limit, it is neutrons, neutron degeneracy pressure. The Pauli exclusion principle again, operating under conditions so extreme that the entire object is, in a sense, a single quantum system. A neutron star is sometimes described as the largest atomic nucleus in the universe, though that analogy only stretches so far. It is a thing without a clean, everyday equivalent. It is its own category. And then there is what the collapse does to the star's spin. You have almost certainly seen at some point a figure skater drawing their arms in. When they pull their arms close to their body, they spin faster. The same mass, the same angular momentum, but redistributed to a smaller radius. And the spin rate increases dramatically. Now apply that principle to a stellar core collapsing from roughly Earth size to 20 kilometers across. The shrinkage in radius is enormous, and the spin rate increases accordingly. A star like our Sun rotates roughly once every 25 days or so. When its core collapses to neutron star dimensions, that slow rotation is wound up into something extraordinary. Newborn neutron stars can spin dozens, hundreds of times per second. The fastest known pulsar rotates approximately 716 times every second, 716 complete rotations per second. In the time it takes you to draw a single slow breath, that object spins hundreds of times. These rapidly spinning neutron stars, particularly those with powerful magnetic fields that direct beams of radio waves from their poles, are called pulsars. When those beams sweep past the Earth on every rotation, we detect them as pulses, ticking with a regularity that rivals atomic clocks. The first pulsar was detected in 1967 and briefly nicknamed LGM-1, Little Green Men, because the signal was so perfectly regular that astronomers initially, half-jokingly, entertained the idea that it might be artificial. It was not artificial. It was simply a neutron star doing what the laws of physics demanded, ticking across the radio sky with the patient precision of something that had been forged in a second and would spin for billions of years. Conservation of angular momentum. The same principle that causes a collapsing gas cloud to spin into a flat disk forming a solar system. The same principle operating at the other end of a star's life, spinning its remnant into something that rotates 700 times per second. Mass is the thread running through everything, but we haven't quite finished, because there is a third death, and it requires one more threshold. The neutron star is held up by neutron degeneracy pressure, but neutron degeneracy pressure has a limit, just as electron degeneracy pressure does. There is a maximum mass beyond which even neutron degeneracy pressure cannot hold. This limit is called the Tolman-Oppenheimer-Volkoff limit, and it sits somewhere around 2.2 to 3 solar masses. The exact value is uncertain. The physics of matter at neutron star densities is still an area of active research, but the existence of the limit is not uncertain at all. If the collapsing stellar core is more massive than roughly 2 to 3 solar masses, neutron degeneracy pressure fails. There is no known force in nature that can stop the collapse, and the matter continues to fall inward, past neutron star densities, past any density we have a complete physical description for, towards something that our current understanding of physics approaches but cannot fully describe, a black hole. The third death. At the center of a black hole, the matter collapses, at least in our current equations, to a singularity, a point of infinite density, which is almost certainly a signal that our equations are breaking down rather than a literal description of what happens. Around that center, at a particular radius, is the event horizon, the boundary, the point of no return. The place at which the escape velocity, the speed you would need to travel to escape the gravitational pull, equals the speed of light. Since nothing travels faster than light, nothing escapes. Not radiation, not particles, not information of any kind. Whatever crosses the event horizon stays. The radius of the event horizon is called the Schwarzschild radius, named for Karl Schwarzschild, who derived it from Einstein's equations in 1916 while serving on the Eastern Front during the First World War, in the year Einstein published his general theory of relativity. A 10 solar mass black hole has a Schwarzschild radius of roughly 30 kilometers. 30 kilometers across, containing 10 times the mass of the Sun, from which light itself cannot escape. From the outside, a stellar mass black hole is not in most circumstances dramatically visible. It doesn't glow on its own. It doesn't pull in everything around it like a cosmic vacuum cleaner. The gravitational field at a safe distance is the same as it would be for any other object of the same mass. If the Sun were magically replaced by a black hole of equal mass, the Earth would continue orbiting it exactly as it does now. We would freeze in the dark, but we would not be pulled in. A black hole is not hungrier than a star. It is just darker. What makes a black hole detectable is usually what happens when it has a companion, a nearby star whose outer layers it strips away, forming a disk of heated infalling gas that radiates powerfully in X-rays as it spirals inward, or the gravitational waves it produces when it merges with another black hole or a neutron star, rippling space-time itself with their collision. But that is another story for another night. Tonight we are talking about the death of a single star, and there is one more variation on the death of the most massive stars that is strange enough to deserve its own moment, because sometimes with the very most massive stars there is no bright supernova at all. The star doesn't explode, it simply vanishes. A candidate for exactly this kind of event was observed in a galaxy called NGC 6946, sometimes called the Fireworks Galaxy, because it has hosted an unusually large number of observed supernovae. A massive star in that galaxy, catalogued as N6946 BH1, was being monitored. It briefly brightened, as if beginning the process of a supernova. And then, instead of exploding, it disappeared. It was there, and then it wasn't. The leading explanation is that the core collapsed directly to a black hole without a successful explosion. The mass was so large, or the conditions so specific, that the shock wave that would normally tear the star apart simply couldn't make it out. The star's matter fell inward without a goodbye. Astronomers call this a failed supernova, a star winking out, swallowed by its own gravity before it could say anything. It is, in a quiet way, one of the stranger things in the universe. Stars spend millions of years burning, building their iron cores, building toward a death that is usually spectacular, and some of them, it seems, just go dark. No last light. No supernova to carry the announcement. Just absence. Mass decided this too. Now, we have been spending time with the most dramatic deaths, the explosions, the neutron stars, the black holes, because they are extraordinary. But we should not leave the fourth death untold, because it is the fate of the most common stars in the galaxy. And it is, in its own way, a kind of immortality. Red dwarfs. Red dwarfs are the smallest stars that qualify as real stars. Those that fuse hydrogen in their cores. They range from the ignition threshold of about 0.08 solar masses up to roughly half a solar mass. And they are by far the most abundant stars in the galaxy. The initial mass function, with the distribution of masses at which stars form, is heavily weighted toward the small. Most stars the galaxy makes are not like the Sun. They are dimmer, cooler, and far, far smaller. Red dwarfs vastly outnumber Sun-like stars and massive stars combined. They are also extraordinarily long-lived. The Sun, at one solar mass, will burn for about 10 billion years total. A red dwarf at 1/10 of a solar mass, burning so slowly, so carefully at such a modest rate, can burn for trillions of years, not billions, trillions. The smallest red dwarfs have calculated lifespans of perhaps 10 trillion years. The current age of the universe is about 13.8 billion years. A 10 trillion year lifespan is more than 700 times the current age of the universe. And this leads to one of the most striking facts in the entire story of stellar life and death. No red dwarf has ever died. Not one. In the entire history of the universe, from the formation of the first stars to tonight, wherever you are, lying there in the dark, not a single red dwarf has lived long enough to exhaust its fuel and reach its end. Every red dwarf ever born is still alive, still burning, still fusing quietly in the darkness of the galaxy. The universe simply is not old enough to have killed one yet. They are functionally immortal on any time scale we can reasonably imagine. And how will they die eventually when the universe is finally old enough to witness it? Not like sun-like stars, not with a planetary nebula, not with a swelling into a red giant. Red dwarfs are fully convective. Unlike the sun, which has layers that don't mix much, a red dwarf circulates its entire hydrogen supply through its core over and over. It burns nearly all of it. There is no hydrogen piling up in a shell. There is no shell ignition. The star simply, very gradually, over trillions of years, exhausts its fuel. Then it contracts and cools. Theory predicts that the smallest red dwarfs will shrink down into white dwarfs, or perhaps more specifically, helium white dwarfs, since they may never get hot enough to ignite helium fusion, without ever becoming red giants at all. No dramatic swelling, no glowing nebula, just a slow dimming over time scales so vast that the word slow stops meaning anything useful. Eventually, a cold, dark remnant, cooling quietly in the dark. No explosion, no pulsar, no event horizon, just a star that ran out of fuel, settled down and went to sleep. The fourth death, the quietest death, and, ironically, the one that takes the longest. 4 deaths, then. The white dwarf, the neutron star, the black hole, and the quiet fade. All of them produced by the same physics, decided by the same number, the one written into a star's future at the moment of its birth: its mass. Below 0.08 solar masses, not a star at all, a brown dwarf. The ignition never happens. Above 0.08 solar masses, up to about 8 solar masses, the star eventually becomes a red giant, sheds its outer layers into a planetary nebula, and leaves behind a white dwarf. The Chandrasekhar limit of 1.4 solar masses governs how massive that white dwarf can be before even electron degeneracy pressure gives way. For the Sun, the white dwarf path is certain. Above about 8 solar masses, the star builds an onion shell interior, fuses all the way to iron, and dies in a core collapse supernova. The remnant, if the core mass falls between about 1.4 and 2 to 3 solar masses, is a neutron star. Above the Tolman-Oppenheimer-Volkoff limit, roughly 2.2 to 3 solar masses for the remnant core. No force in nature can hold the collapse back. The remnant is a black hole, and below about 0.5 solar masses in the category of red dwarfs, the quiet fade, over trillions of years, into a cold, dark remnant. No drama, just time. 4 numbers, 0.08, roughly 8, roughly 1.4, and roughly 2 to 3. 4 thresholds, 4 different endings, all of it decided at birth. Mass is destiny, but there is one more piece of the story, one more thread that connects the life and death of stars to the very specific fact that you are here tonight, lying somewhere warm, listening to this. The universe was born in the Big Bang with essentially 2 elements, hydrogen and helium, in roughly a 3-to-1 ratio by mass, with trace amounts of lithium. That's it, 2 elements. The periodic table had almost nothing in it. No carbon, no oxygen, no nitrogen, no iron, no calcium, no gold, nothing you would need to build a planet or an ocean, or a living cell, or a heartbeat. All of that came later, and almost all of it came from stars. When a star fuses hydrogen into helium in its core, it is doing chemistry on an atomic scale, turning one thing into another. When it moves to the triple alpha process and fuses helium into carbon, it is building a heavier atom. When a massive star burns through carbon, neon, oxygen, silicon in its onion shells, it is manufacturing progressively heavier elements. Oxygen, which you breathe with every slow breath. Silicon, which forms the rocks beneath every ground you've ever walked on. Calcium, which sits in every bone in your body right now. Iron, which runs through your blood. Iron. The element that ends a massive star's life also helped build you. The iron in your blood is not from the Earth's crust, not exactly. It is from stars that lived and died before the sun was born, stars that scattered their material into the interstellar medium, stars whose supernova remnants eventually found their way into the giant molecular cloud that became our solar system. The iron that makes your blood red was forged in the cores of stars. But elements heavier than iron, the ones you cannot make by adding energy to lighter atoms, the ones that require energy to be put in rather than released, those require something else. They require the most extreme conditions in the universe. Supernovae create some of them. The explosion itself, with its extraordinary energy density and its flood of neutrons, can build nuclei heavier than iron by a process of rapid neutron capture. But the very heaviest elements, gold, platinum, uranium, are thought to be produced primarily in something even more violent than a single supernova: a neutron star merger. When two neutron stars orbit each other and spiral together, which happens because they are losing energy to gravitational waves, they eventually collide. And the collision is extraordinary. A kilonova, it's called. A brightness intermediate between a supernova and something quieter, but with a characteristic glow in optical and infrared light from the radioactive decay of freshly forged heavy elements. In August 2017, gravitational wave detectors, or with the LIGO and Virgo observatories, detected the signal of two neutron stars spiraling together and merging in a galaxy about 130 million light-years away. The event was catalogued as GW1 Sambo 817, and for the first time, astronomers were able to follow up that gravitational wave signal with telescopes across the electromagnetic spectrum and watch the kilonova unfold. They saw the glow, they saw the spectral signatures of heavy elements being forged in real time, gold and platinum and other elements scattered through the debris cloud of the merger. The gold, not symbolically, literally. Gold atoms freshly created in a cloud of stellar debris 130 million light-years away. GW170817 was confirmation. The gold in your wedding ring, if you have one. The gold in any ring anywhere on Earth. The platinum in any catalyst converter. The uranium in any reactor. Older than the sun, forged in a stellar cataclysm, possibly a neutron star merger, possibly a very specific kind of supernova, possibly both, scattered into the interstellar medium, gathered into the cloud that became our solar system, accreted into the young Earth, and eventually, over billions of years of geology and chemistry and biology and human history, shaped into a thin band that someone slid onto someone else's finger. The universe made that in a collision of two dead stars. Carl Sagan put it simply and truly. We are made of stardust. The calcium in your bones, the iron in your blood, the oxygen in your lung, all of it came out of stars. All of it was forged in the same fires we have been quietly tracking tonight, from the cold molecular cloud at 10 Kelvin to the iron core that cannot burn, from the protostar shining on gravitational heat to the supernova that briefly outshines a galaxy. You are quite literally the material of dead stars, briefly organized and awake. And here is something worth carrying with you gently as you drift toward sleep. The sun will not explode. This is worth saying directly because it is a thing that popular culture has somehow absorbed incorrectly. The sun, our sun, the one that rose wherever you are today, that warms things and grows things and drives the weather and keeps the inner solar system from being frozen solid. The sun is not massive enough to go supernova, not even close. It is a one solar mass star. The threshold for a core collapse supernova is about 8 solar masses. The sun is missing 7 of those. It will never build the onion shell interior. It will never fuse silicon into iron. It will never have a core collapse in under a second. The sun will swell. In about 5 billion years, when its core hydrogen is exhausted, it will expand into a red giant, large enough to engulf Mercury and Venus, and possibly the Earth. It will fuse helium into carbon briefly. Its outer layers will eventually be shed as a planetary nebula, a glowing shell of gas, beautiful against the sky of whatever survives, and the core will be left behind as a white dwarf, about the size of the Earth, about the mass of the sun, cooling slowly for longer than the current age of the universe. The sun's white dwarf remnant will still be warmer than the cosmic background in 100 billion years. It will still be faintly glowing in 1 trillion, and eventually, in a time frame so long that the word eventually needs to be said very quietly, it will cool to a cold, dark object called a black dwarf. No black dwarf exists yet. The universe is 13.8 billion years old. The time required to cool a white dwarf to darkness is longer than that. Every white dwarf that has ever formed, including those that formed from the very first stars, is still glowing, still warm. Black dwarfs are a fate the universe has not yet had time to produce. They are a prediction, a future the universe is still working its way toward in its slow and patient way. But before any of that, long before the sun swells into a red giant, long before it endangers the Earth by becoming something vast and orange, filling half the sky, there is a quieter deadline. The sun is not static. It has been brightening very gradually over its entire 4.5 billion year life. When it was young, it was about 30% dimmer than it is today, and it will continue to brighten as it ages. In roughly 1 billion years, or perhaps 1.5 billion, the sun's increasing output will begin to push the Earth's oceans past the point of return, evaporating, feeding a runaway greenhouse effect, leaving the surface hot and dry. The Earth will become uninhabitable in about 1 billion years, not because the sun is dying, but because it is still living and slowly growing brighter. The sun's death is 5 billion years away. The sun's dangerous middle age is only 1 billion years away. On the scale of geological time, that is not so very far. The first complex multicellular life on Earth appeared roughly 600 million years ago. We have more time ahead of us before the oceans boil than that. But it is finite. The window for life on the surface of the Earth, under an open sky, in liquid water, breathing an oxygen atmosphere, has a closing time. 1 billion years is a long time. And it is not forever. The universe does not offer forevers. But it does offer this. A star is born from cold nothing, fuses elements in its core, spends billions of years in a patient equilibrium, and then, in whatever fashion its mass has written for it since before its first light, dies and scatters its material back into the galaxy. That material gathers again, collapses again, forms new stars, new planets, new possibilities. The dust from dead stars became the cloud that became the sun. The cloud that became the sun collapsed into a disk, The disk made planets. The planets made continents. The continents made oceans. The oceans made cells. The cells made, eventually, something complicated enough to lie awake at night and wonder where it came from. The answer, the honest, verified, remarkable answer, is from out there, from the cores of stars that burned before the sun existed, from the shockwaves of supernovae that triggered the collapse of the cloud we came from the slow, patient work of gravity and fusion and quantum mechanics running for billions of years in the dark. The iron in your blood was made in the death of a star. The calcium in your teeth was made in the core of a red giant. The oxygen you are slowly breathing right now in the dark was forged in the shell burning of a massive star that died in a supernova before the sun was born. You are here because stars died, and because they died in exactly the right ways, scattering exactly the right materials for the chemistry of life to assemble itself on a small, wet planet orbiting an unremarkable yellow dwarf halfway out in one arm of an ordinary spiral galaxy. Extraordinary does not cover it. And here is the last thing, the thing to carry with you into sleep. The number, the one that decides everything, mass, a number fixed at birth. In the moment a clump of gas in a cold molecular cloud exceeds the gene's threshold and commits to collapsing, before the first fusion reaction, before the first photon escapes, before any light travels in any direction at all. The mass of that clump, written into the cloud by the random compression of gravity, already determines everything. Whether the object will be a red dwarf burning for trillions of years, or a sun-like star spending 10 billion years in careful equilibrium before fading to a white dwarf, or a massive blue star blazing for only a few million years before building an iron core and dying in a second and leaving behind a thing 20 kilometers across that spins 700 times per second. Whether the remnant will cool slowly or pulse across the radio sky or swallow light forever. Whether the death will be a glowing nebula, quiet and beautiful, or an explosion that briefly outshines hundreds of billions of stars. One number, written in the moment of birth, determining the entire biography, from the first light to the last. You set out tonight asking what happens to a star, from the beginning to the end, and why some die gently and some die in cataclysm. The answer is that they all follow the same physics, from the same cold starting point, through the same mechanisms of gravity and pressure and fusion. They only differ in how much they weigh. And that one difference cascades through everything. The temperature, the color, the brightness, the lifespan, the manner of death, the elements they leave behind, the material that eventually finds its way into new clouds and new stars, and, in at least one case, into a creature warm and drowsy and listening in the dark. Wherever you are tonight, whatever corner of the world is dark and quiet around you, whatever your lamp looks like, whether your window shows stars or clouds or the soft amber of a city that never quite goes off, you are part of this. Not metaphorically, literally. The atoms in your body have their own history, longer and stranger than anything a human lifetime could hold. They were inside stars. They were blown out in supernova. They drifted through space for millions of years. They collapsed with a cloud. They accreted onto a planet. They were picked up by chemistry and by biology and by all the improbable things that follow from both. And now, they are here. You are here. Made of the same stuff as pulsars and nebulae, carrying iron forged in a stellar core, breathing oxygen produced in a shell of burning helium around a dying sun. You are the universe looking at itself tonight, wondering where it came from, and the answer is from out there and from very long ago and from the ordinary extraordinary work of gravity and mass and time. We have wandered through a long story tonight, from the cold molecular cloud at -260 degrees Celsius to the protostar shining on gravitational heat, to the long patient burning of the main sequence, to the swelling of the red giant and the flash of helium ignition, to the planetary nebula and the white dwarf settling down to cool for longer than the universe has existed. From the onion shells of the massive star, building carbon and neon and oxygen and silicon, up to the iron that cannot burn, to the core collapse in under a second, to the supernova that outshines a galaxy while spending 99% of its energy on invisible neutrinos, to the neutron star spinning in the dark, to the black hole where light cannot find its way out, to the quiet red dwarf that will still be burning long after the sun is a cold, dark stone. We drifted through all of it, and if you are still here, if you are still awake and listening, that is a good thing. You stayed, you carried it this far. And if you drifted off somewhere along the way, somewhere in the helium flash, or the neutron degeneracy pressure, or the slow trillions of years of the red dwarf, and that's fine too. The stars will still be out there when you wake up. The information doesn't go anywhere. If this slow journey through the sky was something you enjoyed, a gentle like or a subscribe to Calm and Clever means more than you might think. Small channels like this one run on that kind of quiet support. And if you feel like leaving something in the comments, tell me where you are listening from tonight. What time is it in your corner of the world? What does the sky look like if you can see it? I always love knowing where these journeys find you. For now, the iron core is still. The neutron star is spinning, the red dwarf is still burning, as it has been since before the sun was born, as it will be long after the earth is gone. The cloud that made you is still making stars somewhere in the galaxy in the dark. And you are made of all of it. Calm mind, clever dreams. I'll be here tomorrow night.